Okay, so welcome to the second part of my presentation, a practical of how to apply PCA and t-SNE to some real data. What I will do now over the next 30 minutes, so that all the next lectures won't be delayed, is that I will walk you through the notebook briefly and explain essential parts, and then you can yourself explore further, and there are some questions also embedded into the notebook that you can work on and modify and explore how the algorithms behave. Dina just posted the link a few minutes ago. It's a Google Colab. I think you can also just open it and run it on the Google server. And I hope everything will work. I really haven't worked with Google Colab before. So for this practical, we made a selection of 5,000 cells. And for each of these cells, you have information about 1,000 genes. So it's a 5,000 by 1,000 dimensional data set. And here in the beginning of the notebook, there's various imports that are needed, and then some helper function, and the data is fetched from my Dropbox account. These you need to run before, all of them you need to run before we can actually work with the data, but I have already done so now. So the first part of this notebook is linear dimensionality reduction with PCA. So here we will implement PCA by hand. So of course there's also an sklearn implementation that you can use, but just to show you the implementation a little bit in more detail, we will actually use the function to compute eigenvalues. And the data that we will actually work with is this bit here, TASIC 1K log CPN. This is the bit of the data that we will work with, and as you can see, it has a shape of 5,000 samples, 5,000 cells, and 1,000 dimensions. Again, as before during the talk, please interrupt at any time if something is not clear by typing into the chat. Okay, here in the first part, I run the cell where we define a function that computes PCA manual, applied to some data. It's documented, and what it will output is the fraction of variance explained by a particular principal component and the principal component weight vector itself. To do so, you need to first compute the means and center the data, so subtract the means from the data. Then you can compute the variance matrix. And finally, as you may know, you obtain the principal components as the eigenvectors and associated eigenvalues of this data covariance matrix. So this gives you the principal component vectors. The eigenvalues, if you sum them up and divide each eigenvalue by the sum of the eigenvalues, then this is the fraction of the variance in the data that is explained by a particular principal component. And then at the end of the function, we return both. And then after this has been implemented, you can just simply run that on our data set. It takes a few seconds, and so now we can have a look. And a line of code here. I'll just briefly look at what is contained in this variable. So here, this is a long list of 1,000 eigenvalues, and most of them will be very close to 0. I will show you that in a more graphical format in a second. So before we look at how the dataset looks in this low-dimensional representation of the first two principal components, we just plot this fraction of variance explained versus the number of components, and also the cumulative variance explained. And this is done by this piece of code here. And before I explain what the code does, we will just look at the output. So now you see this upper part here. This creates a subplot where the number of the principal component is plotted as a function, or it's plotted versus the variance explained by that principal component. So kind of the importance of that principal component. And then the second plot has the cumulative variance explained, so the total variance explained. So this first plot we can use to see, this is a logarithmic scale here, because basically after the first few principal components, nothing interesting is happening anymore. What this plot tells you is that here, this first point, the first principal components explains roughly 23 or 24% of the variance. The second one explains about 15%. Then the third one explains about 7%. And then there's a long tail with most of the principal components not explaining any of the variance. So by the way, I should have mentioned in the beginning, the data is expression levels of genes. So the data tells you how much a certain gene is expressed into a specific cell. Here, this plot on the right is the total variance explained as the number of principal components used. And so this is basically summing up these values. So we can see that if we, for example, desire to have at least 50% of the variance explained in our low-dimensional representation, then we need at least 5 principal components. So this is implemented here, how to plot that. This also tells us how good a two-dimensional representation would be. So if we take the first two principal components, then this would capture about 40% of the variance in the data. So here's one task that you can do later. So you can compute how much variance is, for example, captured by the first 3 components, or how many, or modify the code to find out how many principal components you need to find 75, 90, or 99%. For this, you can just change the code that we have above. Okay, so we now retain as many principal components as we need to explain at least some % of the variance, and write a function to do so. This is what we have done here. So what this function does is it selects principal components that are sufficient to explain a certain amount of explained variance. For that, we first compute the cumulative variance explained, and then we find the index of the principal component from which on we have at least or we have still less than what we would like in terms of variance explained, and just add 1, so to the next higher value. And then we extract these first principal components that we want to use, and the variance explained terms, and then we return this. So run this cell, and then run the cell in our representation that we have. Now we have these principal component vectors. These are the W's from my presentation before. Now what we need to do is we need to compute the score of each of the data points on that principal component representation, so we can project the data into that lower dimensional representation. And we do that simply by computing the dot product here with this add between the data and the selected principal components. We again encapsulate that into a nice function. And when we apply this to our data, we will simply also save that into the structure as a PCI 75. So we selected so many principal components that we capture 75% of the variance. Is it clear what we did so far? Are there any questions? Okay, not seeing anything now. But now we come to visualization, and that's of course what we're most interested in. So to visualize, we just plot the top two principal components as a scatter plot, and again, as in our examples in the presentation before, the colors indicate the family of these cell types. We just use here a standard scatter plot. When we run that, we get a plot very similar to the one that you observed in the presentation. So you have here these excitatory neurons in green, all the inhibitory neurons in red, and the non-neurons in other colors. When we look at the plot, so the code, there's a question coming up. What are the features variables of the original dataset? Yes. Let me maybe briefly go back to explain that again. I should have explained that better in the beginning. So the data is from a genetic study that measured in individual cells from the brain, measured the expression of various genes. When we look at this entire structure that is loaded, there's actually a lot of stuff going on. So for example, you have all the, so there's various colors that are used to visualize the stuff. There's names for the different clusters that were found there. There's an index of which cell belongs to which cluster. There's all the gene names, so all the names for the different features. And what is important is that the data that we actually use then for each of 5,000 cells, we have the expression level, so the extent to which that gene is expressed in this given cell, as measured with single cell transcriptomics techniques. So this lets us know something about, which receptors such a cell expresses and kind of its interior makeup, I would say. And this genetic identity of the cell also lets you infer something about which cell types or cell class it belongs to. I hope that answers the question. And so these principal components here, these are of course combinations of these original features. So they are combinations of genes. So here, we use the data, so we access the data, and then by modifying here which principal components we show, we can also plot higher principal components versus one another. So if I want to plot the first and the second, the first and the third principal component, then I can do that, and I can see that this changes a bit which features of the data or which classes of the data are distinguished. Well, or which parts of the variance are captured. So these kind of pairwise scatter plots, I think actually also already with principal component analysis, they're already a very good way to visually explore data sets. And this visual exploration process is always very important whenever you do something like clustering. So if you can't see clusters somehow visually in some of the first principal components, then I would be very mistrustful of your clustering. So you can further explore that in an offline task. Okay, now this is already getting close to the end here. Now we would like to Also, of course, apply t-SNE. t-SNE is, if you want to implement that well, it's actually not so straightforward, but conveniently, t-SNE is implemented, for example, in sklearn. So we use the sklearn implementation here. First, we just run it with default parameters. So here we just call t-SNE, or we perform an instantiation of t-SNE with a fixed random state. So this is always important to make your results reproducible, to set the random seed of the random number generator, because in this way we make sure that the layout with which it starts is at least reproducible. Otherwise, every time you run it, you will get a slightly different embedding. Then fit transform here applies t-SNE, so it runs the optimization. And then we just color these in the cluster colors from our original data set. Run that will take a moment. Okay, it's taking a long moment. Maybe our Google servers are busy doing other things. Last time I tried, it took less long. I'm now done. And then I wrote a helper function up above that's a little bit more complicated because we wanted to add all these individual cluster colors. But then you can check out above to plot such t-SNE results. And this is what you get. And you can see this is a reasonably nice embedding. Now, there's a parameter for t-SNE called perplexity. So one thing that one has to say is that the defaults of sklearn are actually quite good. They're now, I think, inspired also by the defaults we suggest in our data communications paper that I also linked for you at the presentation. But you may, for any given application, you may still want to deviate from these standard parameters. So, for example, you may want to set the perplexity higher or lower. Now, if we set the perplexity from 30 to something much lower, let's say 2, can you guess what will happen? There's another question. This was answered already. We'll think a little bit about that while we run the optimization. So what we've seen before is that with a smaller perplexity, yeah, there's a raised hand, Felix. Can you activate your microphone yourself, or do I need to do something? No, allowed to talk, sorry. Here you go. Felix, do you want to say something? So I cannot hear you, unfortunately. Okay, maybe just type your question into the chat or your opinion.
yeah, he has issues with his mic, but he asked a question on the Q&A about what are the features or variables of the original data set.
Oh, but this we already answered like a while ago, no? Again, it's the number of cells by the number of genes that are expressed in those cells. Okay, so by now our optimization here is done with perplexity 2, and keep this picture in mind while I plot the next picture. Maybe we just add a new cell to do so. So you can see here something really odd happens. So now all the data is basically one gigantic ball, and there's lots of very, very small clusters. So this somehow looks not like a veridical visualization of the data. So when you set your perplexity very small, this kind of neighborhood kernel from which on two cells are considered to be similar will be very small as well. So what the algorithm does is it just says like, okay, the cell really wants to keep its very, very, very nearest neighbors, and all the rest doesn't matter. So it completely loses all kind of global stuff. And you can adjust that value. It typically doesn't matter whether it's 30 or 31 or 35. It's more like on orders of magnitude that matters. There's another question. Yeah, very good question. So the original data set has 1,000 features. From the analysis, how many features captures 75% of the variance? And once these features are fed into the t-SNE algorithm, how many features does it return back? So t-SNE is typically run to produce two-dimensional visualizations. So it's also run with two output features. One can change that. So if you here look at all the possible parameters of the function, it has a number of components. Yeah, so you could produce a three-dimensional embedding, but this is very, very rarely does this make sense, or produce anything nice. So it's typically not a good idea. Maybe let's produce a meaningful visualization again. We can go back here to our plot with the number of principal components and then the extracted principal components. So just a second. So let's find out how many principal components are kept for 75% of the variance. It's just waiting to finish below. So for 75% of the variance, we need 43 principal components. So quite a bit, but much less than 1,000 originally. And then actually t-SNE, sorry, can also be initialized with this. And I think this is also allowed here. Sorry. Let's just try if it does what we think it does. So, and use PCA. It doesn't. No, okay. It must be PCA in small letters. So we do that. And run that. One practical tip is that we also briefly covered through the lecture is that early exaggeration can help to overcome global arrangement problems. But in addition, especially for large data sets, can actually be useful to not only have early exaggeration, but have exaggeration throughout the entire optimization procedure. And this is especially important for large data sets. So let's plot this again. So this is after initializing with PCA. It's actually nice because it still shows that these are really quite far away from the rest. These are relatively similar, and it kind of keeps the global arrangement of these clusters. So this is, I would say, this is a much more veridical visualization of the data set than what we've seen before. But what you also see is that with all these visualizations, as a data analyst, you make choices, and these choices are inevitable, but you need to make sure that you're aware of the consequences of these choices and also be able to defend your particular choices by looking at what happens when I change certain parameters. And for TSNE, that is complexity, it's the way you initialize the data, the amount of exaggeration you put in, and the learning rate, which we haven't changed here so far. Some of these factors and the importance of these factors we covered in an article from last year. It's kind of tutorial style, not very math heavy, lots of illustrations on various data sets. I just posted that to the chat. It's called The Art of Using TSNE for Single-Cell Transcriptomics. But I think it's also more generally applicable, and this is what kind of delivers also some of the presets for many of the implementations now. I'm almost out of time. Are there any further questions about TSNE or using it to visualize high-dimensional data or PCA? Okay, I don't see anything right now. I'll stop my screen share here. And yeah, thanks a lot for giving me the opportunity here to present all these things. I hope there was something useful in it for you, and please do not hesitate in case you have questions to contact me and ask about them. We also have implementations of everything with illustrations online on my lab website. So feel free to browse that as well if you find this might be useful for some data set that you're interested in. And with that, I will hand over to Dina and Shal.
Very useful, and it will be really a good starter, a starter tool for people venturing into high-dimensional data. Yeah, thank you very much, Philip. And the notebook is shared, and it will definitely be included on the resources on the GitHub repo for the DSA 2020 for people to have a reference in future. Yeah. Our next instructor is Shalmali Kariuki is one of the trainers and instructors on Data Science Africa, and she's going to take us through exploring R in spatial analytics. So it's really a good continuation from the what Philip taught us on high-dimensional data. Now, Shell is going to take us through exploring R for spatial analytics. Shell, welcome. Yeah.
Thank you, Dina. I'm not able to start my video. I don't know what's up. It tells me you cannot start your video because the host has stopped it. Hello?
Can you try now?
Sorry?
You try sharing now.
Yeah, I think everyone can see me, right?
Yes.
Hi, everyone. Thank you so much for this opportunity. As Dina has mentioned, my name is Shalmali, and I will be taking you through exploring R for spatial analytics. So I have been a member of DSA since 2017 during the summer school that happened in Nyeri, which also happens to be my hometown. And since then, we've maintained this amazing relationship. So I'm very grateful to be given this chance to talk about art. So for those who don't know me, again, I'm based in Nairobi. I was a lecturer before, then I stepped out of academia, became a data analyst, and this is the third year now. I'm currently working as an independent consultant. I tweet at Shell_karaoke. Most of the things I tweet from my handle are related stuff. I'm also a community leader. I lead Nairobi R, that is meetup group we started in Nairobi to sensitize people about R. And I also lead Africa R, which again, the same thing we do for Nairobi R, but then the larger continent. You can read more about us or go through our website. If you look at our Twitter handle at Africa Users, you can check more info about it, about the group. So as I've said, today I'm going to talk about R for spatial analytics. I know we had sessions before dealing with spatial analytics, one with Neil and the other with John. I'm also here to talk about it, but I'm going to concentrate more on R, using R. I won't handle Python at all during the course of this lecture. I might mention a few things just to compare a few things here and there, but this is solely an R session. So one of the things I would want to first talk about, especially for people who are new to R and RStudio. R and RStudio are two different things. R is the software itself, and RStudio is the IDE. There are very many IDEs that people use, but I prefer to use RStudio because I find it efficient and amazing, and the community is just good. So R is the software and RStudio is the IDE. Again, there are many other IDEs, so if you're not willing to work even with an IDE, you can definitely work on R on its own, but using an IDE is more effective. In R, there are things we call packages. I think in Python, there are libraries, yeah. In R, we handle a lot of packages. There are packages for doing different things. We have things like Blockdown, a package like Blockdown for creating websites. For those who follow me on Twitter, or if you just go to my Twitter handle and check my website, it has been built in R using Blockdown. Then we have Bookdown for generating books. A lot of authors in the R community have generated their books using Bookdown. We also have packages like Ggplot, which is used for working with dates. Then we have Plumber, which is used for connecting to APIs from R. We have things like R Markdown for creating amazing reports from data analytics work. And we have family of packages, which I'll be looking at today, that are used for data manipulation in the R community. They are very popular, and they form a system called Tidyverse. Tidyverse is a family of packages that is used for manipulating data, and working with Tidyverse makes analytics so easy. Once you get the hang of the different codes, analyzing data becomes so easy. As you can see, these are, we call them hex stickers. On the right, this is my my laptop. We gather such hex stickers when we attend conferences. It's just a nice way to interact and get to know what people are working on. I use my stickers to kind of remind me of things that I need to learn, although some are conference stickers, others are just small packages here and there. And in R, you can create a package to do basically anything. Like you can create a package that contains a function that greets your colleagues in the morning or reminds people to take a break. So there are very many types of packages. As I mentioned, the tidyverse system is very effective when it comes to data manipulation, especially when you're fitting models. You'll find yourself doing a lot of visualizations, transforming your data, feature engineering and all. So we have different packages within the tidyverse mega package. Something like dplyr is used for selecting rows, selecting variables, renaming columns, sorry, generating summary stats and so on. TDR is used for reshaping data from wide to long and long to wide. We have packages that are used to import different kinds of data sets, for example, SPSS data, Excel data, and so on. We have string R that is used for working with strings, which is really effective when it comes to data cleaning and data manipulation. Then we have forcats for working with factor variables. Then we have our markdown and knitr, which is what we are going to be looking at today for communicating our results. Once you have your analysis, how do you share your results with audience in the simplest way possible? Then we use Ggplot too, which is very good for creating graphs and maps also, but we have other packages for creating maps that we are going to look at today. There are various spatial packages that are used to date, and these are the most popular ones. For those who know about GIS data, we have vector data and raster data. SF is used for handling vector data, while raster is used for handling raster data. Then we have TMAP for creating static and interactive maps, and Leaflet for creating interactive maps. And these are not the only packages that exist. These are packages that are commonly used like today. We have other packages. In R, packages are enclosed in what do you call this? Brackets, curly brackets. So every time you see something like that, it means that's a package. And I started learning spatial analytics, I think at the beginning of 2018. And then a lot of spatial analysts used to use RGDAL and SP. So RGDAL connects to the GDAL system, which is used for reading and writing data. But then I'll talk about a package. I've mentioned SF before, but SF was developed to make work easier. Like for those of us who've used the tidyverse before, SF has been created in such a way that it conforms to the tidyverse principles. And I'll mention some of the tiny principles as we go through our practical. Then there's also the Reshader package that is used for developing 3D packages, 3D visualizations. And as you can see on the top corner, that's a GIF I borrowed somewhere. And Reshader is evolving. It's really nice. It has been developed by some guy, I've forgotten his name, but you can Google about it, and it's amazing. Again, we're going to be dealing with SF a lot today. SF is a package that was developed by Edza, who leads the Spatial Temporal Modeling Laboratory at the Institute of Geoinformatics. He's also the author of applied spatial data analysis with R, the second edition. And he's done a lot of work. He's a big guy in the spatial space, and he developed SF to make work easier for some of us who came, who are learning spatial analytics, having not done a really conc GIS course before. Yeah, so we are going to head over to our studio for a practical session. I know I should have shared a link to the file I'll be using, but I find myself making changes or edits or additions now and then as I present. So I'm going to send a link to my files later, like maybe 10 minutes after finishing my presentation, so that you can look at them. I think that's it for now. I'm going to switch screens. I don't know if we have any question or complaint. I don't know, Dina, if my audio is okay.
You are all loud and clear. Yeah.
Okay,
Thanks.
thank you.
Sham.
Oops, don't want to see that. Close. Just give me 1 minute. Sorry, at times my comp gets tired, so I have to be patient with it. Otherwise, it's going to let me down. So let's wait for it. I think that's the screen I'm sharing. Share. Files. Are you able to see my RStudio windows? Hello, are you able to see my RStudio window? Someone?
Yes.
Okay,
Yes,
thank you.
yes.
Okay, so for those who've never seen RStudio before, this is how it looks. It's similar to Spider for R. And I love working with RStudio because I'm able to see my codes on the left, results of my codes on the right. I can access different files. I can access my environment variables here, and I'm going to clear them. Then I'm able to access my packages, help files, and all that. There are two kind of scripts we use while coding in R. We have one that is a basic script that we can always access using this. So if I type here 2 + 2, for example, and run that, you get the results on the console. But most of the time, when you're working with, like when you're working on data analytics and you want to share the code and the results of the code or the results of the analysis and documentation within that, it's very good to use the Markdown. So this is a Markdown file. I'll show you at the end how we are able to integrate the markdown and the results of the output all together. And it's something I can share with someone without them having to ask me, so like without me having to send so many things in a zip file, like sending the plots or maps, sending the code, sending the documentation and all that. This is something we call a YAML. This is where you specify some things about the document, for example, the title and the author, in this case me, the date, and how you want your output to look like at the end. I'm going to want my output to be a HTML document. So at the end of the day, we are going to do something we call rendering. Rendering is putting your code, documentation, and output all together to produce an output, or rather a file, yeah, an output file. Then TOC, table of contents. I want my file to have a table of contents. So most of the time when I'm creating my YAML, I always insert links to different things. And I use it as a way to, one, market my work and just to show people what I can do, or just to direct them to some of the work that I've done. So as you can see here, I'll have this file, but at the end of the day, once we render the file, if you click on my name, it will direct you to my website. Also, if you click on the title of the markdown, it will take you to the place where the files are hosted. But then there's just a placeholder right now. I've not yet uploaded the files. As I said earlier, I'm going to upload them before. Then our markdown has chunks. This is something we call a chunk, and inside the chunk, that's where we code. So we code inside chunks, and then outside chunks, like this white space here, that's where we write some documentation. So I can say here we are going to read in the data, blah, blah, blah. Think of this as Google Colab, by the way. But then this is not online, so you're not able to edit it as it's not online. Yeah, so at first it's good to always set your universal options, and this just makes your work neat. For example, if you're coming up with visualizations, you want all your graphs to look and feel the same, to have the same height, to have the same width. You also want, I don't know if I have it here. Okay, I don't have it here, but most of the time when I'm working on non-spatial analysis, I set a theme for my graphs, such that if you look at two graphs, they look the same. The only difference is the variable or the information they are displaying. Again, the good thing with working on an R markdown is you can choose to hide your code or show it. But for the purposes of for the purposes of this training, I show my code because it's a training anyway. But most of the time when I'm working on some analytics, the person who contracts you to work on analytics may not be interested in the code per se. So when you say echo is equal to false, the file they receive will only contain the output of the output of the file or the results, but the code won't be shown. So whichever. Then at times there are operations that give you warnings and messages that are not really important. For example, you would load a package and it tells you this is package version blah blah blah, and maybe you're not interested in that. And I'll show you based on something I created the other day. So in R, we use the function library to load packages, which should have already been installed prior. The way we install maybe packages in Python using pip install, in R, packages are hosted on a repository called CRAN. You can read more about it. And to download, sorry, to download the packages from CRAN, we use this command, install.packages. So you install a package once for as long as you have the same computer and the same operating system and the same version of R and R Studio, the same version of R, yeah. And then you load libraries, packages. I use the word packages and libraries interchangeably, yeah, using this. So there's a better way of installing packages. I know someone would ask me, if I have 50 packages, like, will I create 50 lines? No, you don't create 50 lines. But this is a beginner-friendly tutorial, especially given that a majority of participants in DSA are normally Pythonistas. So I wouldn't want to insert something that looks complex, but there's always a function we use that automatically installs a package if you don't have it and loads the package in your current R session. So we are going to use, again, tidyverse for data manipulation. We are going to use SF, as I mentioned. SF binds to GDAL, GEOS, and PROJ. In Py, we have PyGeos. In R, we have RGeos, we have RGDAL, but then SF has all these bindings together. So instead of having to use RGeos, RGDAL differently, you can use all of, you can use SF, which contains all. Then before package developers develop packages, they host them on GitHub or GitLab or Bitbucket, whichever version control system people use. And once the package becomes stable, or once development is done completely, the author submits that package to CRAN, and the guys at CRAN check for different things, like, is your package doing something that another package is already doing? Like, what value add can we see from the package? It's usually a process, and there's a high, I think, I'm not sure, there's a high rate of rejection on CRAN, as I had, I'm not sure. But so before packages are hosted on CRAN, they're always hosted on GitHub. And I recently developed a package that contains the results of the 2019 census, and I'll talk about this, I think, on Saturday. I'll check on the schedule. I'll talk about this, but we are going to be using this package today because it contains a data set I want us to visualize. So KNBS, Kenya National Bureau of Statistics, they published this data in PDFs, and while data is published in PDFs, it's not usable. So this was a pet project I worked on, and I'm very proud of it. Then we have Ggplot, which we are going to use for creating one map, although it's, to me, and this is my personal opinion, Ggplot 2 is a very amazing package for creating visuals, especially normal graphs. I don't think I will ever use any other package. Then we have TMap for creating geographical maps, which are both interactive and static, and Leaflet. Leaflet is mostly known for creating interactive maps. Yeah, so we begin by running these chunks. So if you can see the green, what do you call this, icon, something that looks like an arrow at the end of the chunk, this is how you run different chunks. So we run that, and then we run this. So once we run that chunk, it loads all the packages that I want to use in this session. And it's always good to load your packages at the beginning of the script instead of having to load packages below. One disclaimer, I have a very weak, I don't know whether to call it weak, my laptop is not really strong. So sometimes it's very slow at times. I was just struggling with it an hour ago, so be patient. There are things I might skip, one because of time, but because I know this comp may not be able to handle. I may need a computer donation soon, but right now I'll work with this. Yeah, so from the SF package, if you just come to the console and type SF, it lists a whole lot of functions that are in the SF package. And I don't know a majority of these functions, and I don't use a majority of them. And if you want to learn more about them, you can always, for example, if I want to learn more about STJoin, I think this is something Neil mentioned when he gave his presentation. For you to look for, to do that, it gives you definition, blah, 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 and examples down here. But if you've already loaded your packages like I have done, you don't need to do that. So this will still open up a help page, but you can always come here and type the help function there. So when you're reading in, we are going to use data the Kenya, so shapefiles. What are shapefiles? Shapefiles are like data that contains geographical boundaries. So I'm going to use Kenya counties shapefiles. And later we are going to merge this data with another data set to visualize it as a map. So there are two functions that are used to load shapefiles in SF. You can either, you can either use st_read or you use read_sf. And allow me to just use this so you can do that. And it registers at the environment over here. And if you just click on this drop down arrow, you're able to see the kind of variables that it has. I'll show you another way of doing that. Now, this is tricky. The last column, which is a geometry, it contains the polygons. So this data contains boundaries for each of the 47 counties in Kenya. The last column is a geometry column. It contains the coordinates nested in list of lists. And it's very difficult to visualize this data. So I'm going to visualize at least, I think, the first 5 rows. And this will kind of take some time, like 5 minutes. I know we don't have time. Let's see how long it takes. I hope my comp does not hang. So you can always place your cursor over here and run. Let's see how long it takes. I know this is an awkward moment of silence, but this is the only time I'm going to be visualizing this. So just give it a minute or two. Again, this is not anything to do with R. I don't want skeptics to go saying, oh, R takes time to open up geometry. I'm like, no, my comp is really small. Like, I wouldn't even want to tell you the specs. It's small, but this is what I wanted you to see. Each row represents a county. For those who are, I don't know, conversant with Kenyan boundaries, we work with counties, and it gives us information about the area and perimeter of each county. But at the end, this is what is of importance to us: the boundaries, the geographical boundaries in terms of coordinates. So this forms a polygon. So we have a polygon and a polygon and so on. I just wanted to show you that. So I'm going to close that and comment this out. What we do, if you want to visualize the whole data and you don't want to, and you know the geometry variable or column will make your comp hang or whatever, there's a function called st_drop geometry. And we have this function, which is a pipe operator. A pipe operator is used to define sequential processes. For example, I will say, I woke up, Control-Shift-M. Then what did I do when I woke up? I checked Twitter. Then I had a shower. Then I had breakfast and so on. So it's just used to denote sequential, sequential processes. So like, imagine you have a data set, a data frame, and you want to drop some variables. You want to rename a certain variable. You want to filter some rows. You want to calculate maybe the average age of a certain group of people. You can do that in one line of code using these connectors. So this is what we call a piping operator, and it's part of the tidyverse system. So here we want to take our shapefiles. We've given the name Kenya SHP, and then from there, we drop the geometry. Sorry. Okay, sorry. And then view this. So if I just run that, right now it is very fast because we don't have. Dina, are you saying something? I can hear someone on the background saying something. I'm not sure. Hello?
No, it's all, no, it's quiet. You continue. Okay. Yeah.
And I'm sorry for the background noise. I live near a garage and a center that makes, I think they are tanks. There's nothing I can do, but I hope I'm audible. Anyway, so as I was saying, once you drop the geometry column, you can easily visualize your shapefiles. So in this case, if I want to visualize my home county, which is Nyeri, we have the area, perimeter, blah, blah, blah. What you have to know or remember at the back of your mind is that there is an additional column at the end that contains the boundaries of each of the records, but we've dropped it so that we can be able to see how our data looks like. Okay, that's one chunk. And the chunk was talking about reading in Kenya boundaries. So you can either use method 1 or method 2, whichever works. Then if we want to inspect a few rows, you can have head of that. And there's this output here that shows you different things. It shows you the CRS, which we're going to mention below, the boundary boxes, and the geometry type, which is a multi-polygon, because it is like a polygon of polygons. But what we're interested in is the first 5 rows over here. So you can see the ID, the area, blah, 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 the shape area, and the geometry. We've seen this geometry. We are going to look at this geometry in a better way in a few. Then to look at the column names of the Kenya shape files, you can either use call names or use names, whichever will work, and it gives you the names, the columns that are in that data set in the shape files. Also, we want to look at Kenya shapefile, the class of the shape files. So there are 3 classes that are used to represent simple features. So SF is used to represent the whole table. As you can see, the shapefile itself is an SF object, which is also a data frame and a table. So you can read more about tables and table_df. Then within that shapefile, we have that geometry column, which I've talked about, and it is of class SFC, which is the last column. And then that column is like a column of different rows. So each row is a record. For example, the boundaries of Nyeri, that will be of class SFG. We're going to look at that in a bit. So this is very important to just see whether your data is in SF format. And then to look at the variable types, can use glimpse. So it tells you have 47 rows. We have 47 counties in Kenya. We have 47 rows and 9 columns. And for each of the columns, it gives you the data type. You can see the last column here, which is the geometry, is a multi-polygon. Then you can extract the geometry column. So st_geometry, remember st_geometry in R. If you want to see in which package a function belongs, you just type the package, not the package, the function, and you can see at the end, it tells you it's from that package. And this is only possible if you've loaded that package before. So we want to extract the geometry. You can see it's a large SFC multi-polygon. I've talked about the SFC class because it's the last column. And it's nested within a list. So if we want to see the first one, let's see whether we are. So this is just one, let's say Nyeri, this is just one record. And that's why it becomes very heavy. So this is just one record. This is a polygon for one county. And so we have 47 of such sets. And then again, as I've mentioned, the geometry classes have their own, the geometry column has its own class, which is SFC. And we know the geometry object we've just produced here is a list. In R, when you want to obtain the elements of a list, for example, the first list, you use double square brackets and then the position. So this is first, this 2 will be second, N will be end, and so on. So for you to see the class of each of them, it becomes SFG. I normally ignore these others. I'm just interested with SFG. So one of the things that we need to take care of when working with spatial data is looking at the CRS system. which CRS is just a way in which the data has been used to, like how the data is represented on Earth. I'm not a very big guru of CRS functions. All I know is that there's this one 4326 that is used globally. I know maybe Neil would have mentioned that on his code. So we use this, but from what I know, my shapefiles are already in the format, the CRS for 4326 format, and which is this. But if we can look at it in a better way, even without fast transforming, you can see it's in that. You can read more about what each of these means. And I've stated in my file, this line is not necessary since the shapefile is already in this, the WGS84 format, which is the CRS, but it doesn't hurt to run again. It doesn't do any harm. Anyway, yeah, that's the first part. And then we are going to be using data from the package I build. So just to reload the package, it's already loaded anyway. It's called our Kenya Sensors. I lacked a better name. So one thing you're going to notice when you load, okay, it's not loading right now. It gives you, what do you call it? There's a message you're supposed to get at the end of the day. Let me try detaching it, just a minute. Yeah, so this is a message I put in, and this is not being selfish. I just need people to cite my work whenever they are going to use my data sets. And if anyone has a problem with any of the data sets, they should just feel free to reach me on that email. Anyway, so once we've loaded our Kenya sensors, there is, for you to see the tables that are in this package, ideally packages should contain functions and data sets, but this is totally a data set package. It has all the data sets as they are in the published files by KNBS, but there's this data, so let's give it a name, let's call it DC, that acts like a code book. So if you look at DC, it gives the data set, the volume in which the data set belongs. So KNBS published this data in 4 volumes, the specific table and the description of the table. But also, when I was creating, I attached help files. So if we want to see more about this data, you will just type that and it gives you a description and variable names if the variables are not really intuitive. So there are some I didn't need to give, but as you can see, just the way the data is in the files, or maybe a cleaner format. So today we are going to be looking at a table on disabilities, which is in volume 4. It's table 2.27. If you look at the published data, I'm going to give it a new name, which is disability_DF. And for us to see this data, it contains the counties, sub-counties. Admin area shows whether the area is a county or sub-county. And for example, if you look at Mombasa, well, let's look at Nyeri. Sorry, I love my hometown very much. These are the sub-counties in Nyeri, including some forest areas. So the very first row of each county is the summation. So this is the total of all the sub-counties in Nyeri. So if you will add up these, you should be able to get the first row. And here we are assuming that KNBS was right, like it did not make any errors, because I tried looking at some of them to look for errors, but that again is not my work. My work was only to show this data. Again, I'll talk about this on Friday, but this is the data we are going to be looking at. It's disability data for each sub-county. And the disabilities that are handled here are vision, hearing, mobility, cognition, self-care, and communication. And for each of the impairments, we'll have a variable showing total, then male and female. So we want to clean the data so that the counties match those in the shapefile. So if you can see, we have this data, but it doesn't have the geometry column in it. We want to join this data to the Kenya shapefiles data. We want to join, and we are going to use the county as the main variable for joining. But what you're going to notice is the counties, the way the counties are named are different. So for example, if we look at the unique counties in the disabilities data, you will notice that they are in caps lock first. And just to mention, unique is a function that is part of the deployer package. We have unique base and unique deployer somewhere. So we use it to generate unique values of variable. So you can see they're all in caps, right? That's the disability data. Then we want to look at the county names of the shapefile. But remember, we are going to drop the geometry variable for obvious reasons I had already explained. So we'll take the shapefiles, drop that for now, select the county variable, then pull. Pull converts a data frame of one variable into a vector. Then we get the unique counties. So if I run that and take that, copy paste there, you notice this is in small caps, and I really like the way this looks. It's title case, but all this is caps. So what we are going to do, we are going to make this, the counties in the disability data, match the shapefiles. Because these shapefiles are universally used. So at the end of the day, you want to produce something that, like when someone looks at the shapefile, they're able to see. Then there are things you will notice. For example, in the shapefile, we have Keyo Marakwet, but in the data, we have Elgeyo Marakwet. In the shapefile, we have Trans Nzoia separated by a space. In here we have Trans Nzoia, oh, that's okay. Here we have Taita Taveta with a stroke. Here we have Taita Taveta. We have Taita Taveta, yeah, with a space. So those are some of the things we are going to be cleaning. So first of all, we need to convert the disability county names to title case. Title case is where the first letter is capital, the rest is small. So we take disability DF, we ungroup. So what happened when I was creating these packages, I was creating groups. Like when I was cleaning the data, I was generating stuff based on groups. And for some data sets, I forgot to ungroup. So I need to ungroup right now. But that's not really a big issue. So run, I can see time is not on our side, then look at the unique counties again. At least now they match, but then we need to take care of the differences in the county names. So where we have Taita Taveta, instead of the stroke replaced with a space, so we'll use if else command. Mutate is used to generate new variables, but I don't really want to generate a new variable. I want to rewrite my current variable. So Tharaka-Nithi, Tharaka, Elgeyo, blah, 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 Nairobi City to Nairobi. Everything else remains as it is. And then there's this code here that checks which of the unique counties in the disability DFs are not in. So this is in, and you have an exclamation here, are not in the counties shapefile, the counties in the shapefiles. So you have XXX, which is okay, because I put that to show, if you look at the first 3 rows of the disability DF data, it shows the total, the country total, and the total split into rural and urban. And definitely that's not like the county. I would have even written that as Kenya, but that's okay. That's not in the other data set, which is fine. We are good to go. Both the counties in the shapefiles are now matching the counties in our disability DF. And now we can use that variable to merge. What we're also going to do is I only want, since I have the shape files we have are county level shape files, and our disability data is sub-county level data, we are going to filter rows to only be left with counties, to only be left with where the admin areas being counties. And once we have that, we are going to drop the sub-county and admin area. So let me show you the results of that. We are going to store this in a new variable, not variable, in a new data set called disability df2. And when you look at it now, we only have the county level data. So we have counties, which is 1 to 47 for each of the variables. Now, after that, we want to join the two shape files, not shape files, the two data set. One is a shape file of class SF, the other one is a normal data set. And here we are going to use a normal join. So I don't know if we are all familiar with joins. We have left join, inner join, full join, right join. We can also have, there's also, like when you have two shape files and you want to combine them together, we do what we call spatial join. And in R, or rather in SF, spatial join is given by that function. Like you use st_join to join two spatial data frames. But now here, we want to join a spatial data frame, which is Kenya SHP, with a non-spatial data frame or a normal data frame. I'm so used to saying kawaida. When I say kawaida, it's normal. And I want to merge by county. But what you're going to realize is in the disability data, the name of the county is different. Like, oh, just a minute. It's county with capital C and all the others are small. And then in the shape file, it's all caps. So what we are going to do is we are going to rename our small, so the rename function is rename new var is equal to old var. So we want to rename county to county with capital letters, which we do that. And then we'll remove leading or trailing spaces, because if Shalmith being equal to Shalmith, that's false. And if you're not used to programming, you will be like, but Shalmith is Shalmith. You're like, no, there's a trailing space over here. And sometimes our naked eye is not able to see this, especially if you're looking at data like this as a data frame, you're not able to see a leading or trailing space. And such weird spaces can mess you up big time. So what we do, we remove spaces using this function. There are many, there's a tidyverse function for doing this, but there are some of these functions that are in base R and I'm used to. So once you do that, now you're good to go. Your counties match, so you carry out a join. So it's a left join where the first data needs to be the shapefile, then your normal data frame, then your margin variable. So once we do that, run, you see the data over here, and now the data has 47 observations, but it still has 47 observations, but with 27 variables, because we've combined the variables for the shapefiles, which are the first half, and the other, sorry, and the variables for the disability data on the last part. And then I want to order my data so that county appears first and then everything else follows. So select is used for selecting variables, but you can also use it for ordering your variables. So we have county, which is the first, then everything else follows. So once we do that, run, we have now county as the first variable. And because of what I said earlier, now our matched DF has a geometry variable, and it will make my computer hang, and I don't want that. So if you have a very strong computer, you can always run that, but for me, I don't. So I can view this having dropped the geometry variable. So again, Nyeri, so right now we have shapefile data for Nyeri as the first half, and then the disability data as the other part. So what we've done, we've dropped a variable geometry, which ideally should be between this column and this column. So between column 8 and column 9, there should be a geometry variable, but because I don't want my computer to hang, we've dropped it. So again, when you check for the class of your merged DF, it should be an SF, which is a data frame. And then columns of the merged DF, now they are like columns from the shapefiles and columns from the, what do you call this? The other data, the disability data. Then we've done that. And then now glimpse, looking at the variable types. When I was cleaning this data, I tried as much as I could to make sure that numerical values are numeric and character variables are characters. So we don't have to do any much cleaning right now. So visualizing the data, before packages were developed, people used to visualize data using base functions. So we have a base, a plot function where you take the shapefiles, select geometry. So in R, we use the $ to select the variable in base R. I know if it was Python, let me try my Python skills. We will do these and then put something like that. But in R, we use the $sign. Then this shows you the type of line, the type of boundaries you want, and the color you want. So we can have that. We can change this to, I don't know, let me try changing it to brown. You can also use hex codes. So on the internet, there are very many color codes. You can use whichever they are compatible with R. I won't spend so much time on this because we rarely plot using this plot. I'm going to move directly to Ggplot, which is a function or a package. Ggplot2 is the package, but Ggplot is the function. Ggplot is used for creating amazing visuals. But when it comes to maps, I would rather use T-maps and leaflets, which we're going to cover next. But anyway, for the purpose of this training, we are looking at the data. So Ggplot is the function. The data is the merged DF. Here we have to specify what kind of plotting we are doing. We want a geom_SF. So once you type geom_, you can see so many types of graphs that you can come up with. So right now, we want a map, so geom_SF map. IS, aesthetics, explains some of the things like what do you want your geometry to be. So my geometry is the geometry column. And I want to look at, we are going to analyze vision total. Vision total is just one of the variables. And I picked this arbitrarily. There was no reason behind it. Then sometimes you just want to override the theme that R provides. Let me show you. If we just run that, it gives you a basic map like that. I don't like the theme. So what we do, you remove the theme using theme_void. And when you run that, be quick, it gives you that. So it has removed the background theme, the grayish panel background that I didn't want. Then we want to give our title, our map a title. I'm not really good at titles, but anyway, that works for now. And you can also give your plot a caption, which kind of owns, it's like owning your work. And then change the theme of the map. So you want your plot title to be of a different font. This is the font name I chose, and to be a different size, and to be placed at the center of the map, top center, like justified at the center. And then we don't want our legend to have this name, vision title. Already the title will, vision total, the title will speak for itself. And also for my plot caption, I also want it to be of this font and size 12. And then the coloring system. So I'll show you two. So there is one from, which is Viridis. I don't know how to pronounce this. You can read about it later. It produces the map in like a purple, yellow, green kind of palette, which I think is beautiful. So this is, I think this is, I don't know which county this is. I'm not very good with these counties, but we can also choose to use our own specified color. So I want to create a gradient that ranges from dark green to red. So you can have something like that. It's up to you, like the way you want your map to look like. I don't know, Dina, how many minutes do I have? Are they 5 or 10?
5 to 10. Yeah.
I thought so. Okay.
Yeah.
So I'm going to hurry at this point. Then we have team maps. So you can set team map. You can set team map. Sorry, you can set the mode to either view or.
Sorry to interrupt. There is a question from Felix asking the data set with the geometry info. Is it also part of the RR library that you created?
Thank you. So there are shape files. I think he's asking about the Kenya county's shape files, no? Is it the county?
With the geometry info, that's the shape file.
Yeah,
right?
that's the shape file. Yeah. So how do I put it? The package has the shape files, but I later got other shape files, so I should replace. But then I didn't want to replace, especially for people who have started using the shape files that are already there. So it depends. I think there are 2 or 3 kinds of shape files floating around, because there are some that are in the package and they're a bit different in terms of how the counties have been named. They're a bit different from what we have here. But what I do when I share this, I'm going to share the Kenya counties, this folder here, and the script. So you can choose whichever. The information is still the same. The boundary values are still the same. The only difference is how the counties are written. I think that answers the question. So team map, you can choose to either have it as view or plot, which sets the mode as either static, that's plot, and view, which is interactive. Team map contains several functions. So team m_shape, that's what you use to define the data set itself. Then tm_fill, it fills the polygon. You can either fill with one color or fill it with a variable. For us, we want to fill it with the vision total variables, because we want to see which areas have more people with vision impairment as opposed to the other. You can choose a palette. We are going to use greens. Give the title, and I added this because my map was having issues at some point. Then the borders, I want the borders to be color red, and I want them to have, I think this was dashed, a dashed kind of feeling, a dashed line. I don't know if there's any other name for dashed. I don't know why we have 2 titles. One should work, one should not be here. And then legend position, we want the legend to be at the left bottom, but this only works if your map is in the plot mode. Otherwise, it will always be put on the top right. Then this adds a scale bar, and this adds a compass. So if I want to change this to, I had already run this. So this is the plot you have when it's a static mode. That TM mode is equal to plot. When you change it to view, it becomes different. I have 1 minute and I still have content. Run, 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 run. Again, this is not an R issue. It's my laptop. So this is how the static mode looks like. And I think it's really pretty. You can choose to choose what kind of map you want. So if you want like an open street map, blah, 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 whichever you want, that's okay. Then the last, remember you can play around with all these options. Like for example, if I didn't want greens, I wanted any other palette, I can easily choose that. Then we have leaflet. So leaflet is used a lot by people who are working with R and spatial analytics. So this specifies the color palette. Then this specifies how you want the labels to look like. Let me run a bit of that so that you can see. Like I want each, I want when I hover around an area, for example, Nyeri County, I want the pop-up to look pretty. So I want it to tell me which county it is and the value. So leaflet comes from the leaflet package, and the function is also called leaflet, which takes in the data. Then it add tiles, then add polygons. You want your polygons to be color red. You want the boundaries to be dashed. You want to fill the color with this palette you've created here. So this is what we do. When you highlight, when you hover around the county you want it to highlight as red, blah, blah, blah. These are just options. Sorry, because of time I have to rush through. You can read more about the leaflet function by just typing leaflet on console. And it gives you a lot of documentation, things you would want to know. Anyway, so that was the last part of this. So I just want to show you how it looks like. And please behave. Cool. So you can see, let me try and zoom in a bit. You can see as I hover around, where is our county? Here, it tells you it's that county and it's the value. So the darker the region is, the more impaired people in that county. You can change the breaks of this legend. Please read how to. So at the beginning, I said we are able to consolidate all this together. So once I have my code, my output and everything, and I'm good to go, I will come at this point here and say need to HTML. We call the process rendering. So it will render. And I want to show you how it looks like on the web browser. It's going to create a pop-up. I don't know whether you'll be able to see the pop-up. Let's see. So this is the process of rendering the file, which is just combining code and output and documentation together. So if your file has an error, this process will break at some point. 97, 900. Then once it's done, you should wait for a pop-up, which is what I'm waiting for right now. I don't know, Dina, can you see the pop-up? Sometimes when I'm using two screens and I'm not able to see what people are seeing.
Yeah,
you can see the pop-up. Yeah, so this is how our document would look like. Again, remember, as I said, when I include links, so you can click on each of these links, it will redirect you to some place. And then the table of contents, especially when you're working on a large analysis, you want people to be able to go specifically to a certain place. And then your code, remember I choose to show my code, so you can see code, output, code, output, code, output, the plots. And for our interactive plots, they're still interactive on HTML. So you're still able to do this. I also insert this to just show it's the end. So yeah, I think because of time, I'm going to stop there, but I just wanted to mention, once we have these, you can always open this in browser, or I can even send, I don't know if I'm able to even send something on chat right now.
Yes, you can. And actually there has been a request for you to share
Oh,
this.
really?
Yeah. Yeah.
I'm going to share the source code. So I'm going to publish this on the website and send my link, send my code to share my code with you people, so that people can access the code and the, what do you call them? The code and the output and the shape files. I wanted to just quickly share the HTML file, but I'm not able to right now, which is okay. So one example, one good thing about using leaflet especially is that when you're creating dashboards in R using a package called Shiny, you can easily embed them. And I just want to share only one screen, Dina, before, just 1 minute, just to show one slide, so that people can save the links. Share. I just wanted to show this. So please go through. So there's a way you can share your files. So for us, we've rendered directly from Markdown to HTML. You can always render it as PDF or Word. You can share your work as a Shiny dashboard or app. I want people to look at these two links. One has been built by the Kenya Red Cross. So they used the data to come up with, I don't know, an amazing dashboard using Shiny, and it has leaflet maps. They've used R, and it's amazing. Then the first one is something I built. It's still a bit slow. I'm trying to optimize it, but I'll talk about it more on Friday when I talk about the package. And that's the end for me.
Yeah, thank you very much, Shell. That was really enlightening and inspiring for people to use R. It's a very powerful tool for research. So is Python. Yeah. So thank you very much, Shell. You will share the source code, and we'll definitely share it with the DSA community. Asante-san.
Okay, thank you.
Yeah.
Okay.
Okay, our next speaker is Nasia Ntala. We already have her online. She's a data engineer at Facebook. You're welcome, Nasia.
Hi, everyone. I'm really excited to be here. Can I start my video?
Yes, please. Martin, she can share, right? Her screen. Yeah.
Yes, she can.
Yeah. Okay. Yeah. Please go ahead, Nasia.
Hi, thank you. Thank you so much for inviting me here today. It's really exciting to have this event even online. Yes, so I'm Nasia. I'm a data engineer in Facebook in community integrity. I've been with Facebook at London for 2.5 years now, and I will try to give you some insights today about what do we do at Integrity, what is a data engineer role. It's really close to data science, so maybe some will resonate and will relate to that more. Okay. So today, what I will try to cover is about what is integrity at Facebook, what type of integrity solutions we are building, what is data engineering, some of the trade-offs that we have in data engineering in the scale of Facebook with the amount of data we have, and also what does it take to become a data engineer. So the presentation will be for around 40 minutes, and I will leave some time at the end for questions in case you have anything you would like to ask or something you're interested in. So integrity at Facebook, we have a very, very big team that tries to make sure that we minimize bad experiences and try to make Facebook and all of our platforms a safe place. And what do we mean by bad experiences is that anything that causes harm, or things like fake accounts, scams, or even maybe very often we have like even worse cases like online crime and things that might go wrong. And it's all really new in terms of we try to build all of this integrity space online, but it's actually a very novel space for our society and for the world. So we really try to collect all the voices and hear everyone's experiences and try to do our best for that. So just to give a bit of context for how the structure works for integrity at Facebook, for the problems we have a team, Community Integrity. This is the team I'm working on, where we build technology at scale. And we have different problem areas, and each problem area try to understand the problem and build classifiers or detect adversarial behaviors of user, and try to enforce community standards at scale. Community standards now they're developed by a team that is called content policy. So imagine there is many policy makers, and try to create the policies that say, okay, is this right or is this wrong? What does fake mean? What does coming mean for a user online? Or like maybe some, maybe you've seen like nudity or things like this are not allowed, and we are removing them from the platform. So there are different policymakers from all over the world that try to define what is right and wrong. And also it might be different in every culture at some point, because some countries might have different policies than other countries. And then we have our community operations team, where they enforce these community standards, but with human review. So our community integrity team tries to automate and build things at scale, but of course, this is not easy for the amount of users and for the amount of problems we have. So we have a very big team that goes through human review and check on their own, like if this is bad or it's not bad for our problems. So what do we try to build as a community integrity? We have different things. So we are building user experiences. So if you've seen online on Facebook or Instagram, for example, if you think that something is bad or is harming, then you can give us feedback, or you can report it to us, and then we will send it to human review. Sometimes, if we do by accident, we might remove an account. We build appeal systems so that you can come back and appeal the decision we've taken, and then again we will review it, and accordingly your account might come back. And we also have warning screens or ways to inform users that, okay, this is a content, for example, that it's not good, you might not want to see it. Are you sure? Or this is a content that might not have correct information. So try to also have this warning to bring user awareness. And then we have also self-remediation tools. So on your own, you can block, hide, or unfollow users that you don't want to see and you think they're not good. And for tools and technology, we build machine learning classifiers, lots of machine learning. Our teams are massive on building ML. And also we build a lot of infrastructure for review and media matching services. So the team I am working on is impersonation. So we are a big team in London. We also have people in California, Austin, and in many places in the world. And we try to find ways to understand what is impersonation and if a user is pretending to be someone else. And I'm not sure, like potentially you might have many from the feedback we get from the users, it's a very big problem. And it's so often that we actually might see people pretending to be famous people, famous accounts, or even private individuals, or even just misrepresenting themselves. So for example, if you see in this screen, so many people say, I'm a software engineer at Facebook. And once when we looked at the data, we saw that Facebook is actually the most popular workplace that people put on Facebook, which might make sense in a way, but all these ways of trying to misrepresent yourself and try to pretend you're someone else, this is what we are trying to do and find. And it might not seem as a very harmful problem at the first sight, but actually it might be really harmful, because when people hide their identity, it means that they might want to cause some other type of harm. It means that they might want to forge someone's identity, or they might want to, you know, scam people or take your own, like maybe they do a finance scamming, or they might ask you to, you know, sometimes they say, oh, we are having giveaways, and then they might ask for your details and then find a different way to work around them, the scamming process. So we really try to be on top of the funnel and find these accounts before they cause harm, real harm to users. And it's often like our team sees very often, mostly for high profile people, you know, things on the news, and like The Rock says, warns fans about Facebook scam, and they say, be smart, vigilant, and don't engage, because this is something that it's really, really happening. And we get all the time requests, and all the time we get this big media, media fires, and we want to be very proactive. We want to be very, we want to find them really fast, because they can cause actual harm to our users. It's not just the impersonation, but it's all of the scams that is caused downstream. And also, we have so many users, so they always find different ways to engage, and they find different ways to cause this harm, you know. So we used to find, you know, when it's the same name and the same photo, it's really easy to detect. But as soon as, for example, users might use the name of a famous person but a different photo, then it becomes more complex, and we have to find different ways of understanding, okay, is this bad or not? And also try to also see in different cultures what is right or not, because, for example, we found out that people in Latin America, they might very easily turn the names to a football player because they're really, really fans of them. So we don't want to actually remove these accounts, because they're doing it for a good reason and just because they're fans. But we want to understand what is the line, where do we draw the line of what is bad or not in impersonation. And just to give like a bit of context, our platforms, when we talk about Facebook, it's not just Facebook. We have a lot of different products and a lot of different ways that we engage with people, right? All of us. So Facebook platform has 2.2 billion active users every month. Instagram has 1 billion active users. And then we have WhatsApp, that it's also 450 million statuses every day. And also many people engage on groups or with Messenger, and we have so many photos uploaded daily. So our data are massive. If you imagine all these engagements and all these interactions that are happening from every user every day, imagine how much data we need to understand, how much different behaviors we need to put together, and also connect all the different dots, right? From groups to Facebook and to Instagram. And our teams are working on all of the different problems. So it's really, really important to keep, for us, for Facebook, the vision is to keep connecting the users, to allow a safe space to be there for everyone, build community, and bring the world closer together. So that's why integrity is such a big thing, and we are putting a lot of efforts and investing a lot in integrity and try to solve these problems, which they're never really solved, to be honest, but we want to be ahead of people who try to harm, and we want to be ahead of hackers or all of the adversarial behavior that's happening. So with all of this data, with all of these different platforms, we really want to learn from our users. These are some of the biggest questions we have, and that's why Facebook really appraises diversity and really tries to hear all voices from all different countries of the world, from all the different areas. Since it started as more as a US company, now it's trying to expand to all over the globe, because in order to build products that are applying to so many users, you need to hear all the voices. And this is something that we try to keep getting feedback from people and keep improving our policies, our processes, and everything we do. And we want to understand all the different problems and like all the different ways that people are behaving. And it's not always easy because things keep changing. It's a very dynamic product and a very dynamic relationship that we have with our users. So we always try to find, like, you know, what's weird happening in a different location, why this segment is behaving different from the other. We have a lot of different questions and a lot of different markets to explore and understand. And yeah, it's fake accounts and all of the harm happening online is a very, very big and serious thing. And we are trying to protect everyone. So some of the things we are building in community integrity. So I'm not sure, maybe you've seen how our reporting flows work. So for example, if as a user, that's how we get reports from the users and input from the users. So you can go to any account or any content and you can say, okay, I have an issue, I want to report something. And then you have different tags you can select. And this, we keep evolving them, we keep adding more things. But for example, these are some of the examples that you say, okay, pretending to be someone, it's a celebrity, a friend, or they're pretending to be me. And then you can select, if you select a friend or a celebrity, you can select which celebrity is that. And then you have different actions that you can block, and you can hide everything, or you can put an additional report. And we have these tags for also different problem areas, like fake accounts, fake names, or if you say they're posting inappropriate things, they might be harassing you. And you can also ask help if you cannot access your account or anything else, and give us a free feedback form, and we will look into it. So these are one of the reporting flows we have built, and we really take care of, and we're looking into. And we have also different ways to we are trying to think of different ways to make users more aware. And what does that mean? We want to make sure that users will know if something is bad or not. Because if we don't have the capacity, and if we cannot, for example, get all the input from users, if we find that, this is for Instagram, if we find that an account, for example, it looks very similar to another account, but on Instagram, there is no such thing as necessarily impersonation, because any user can have multiple accounts and you can have different names. So we want to try to bring awareness of, okay, is this actually a fun account, a commentary account, or is this an account that is trying to harm users? So that's why when we find these edge cases and we are not sure, for example, this is Lady Gaga official, but there is another Lady Gaga account. So we ask the user to say, okay, you have to put in your page that you are a fan account. So at least users can connect you directly with the original account, or that you're a commentary account. In that way, we try to bring a bit more visibility of the different types of accounts and make our end users understand a bit more who is the real authentic account and who is not, and then it's their choice to follow or get more involved with these accounts. And also we have built a verification process. So probably you've seen this blue tick in Facebook or Instagram. So once accounts have more than a specific amount of users or followers or friends and a lot of content and it becomes viral, then we try to enforce them to confirm their identity. So we've built all the verification process and we ask them to give us some proof of identity or go through some challenges so that we can actually verify for our end users who is the real account and who is not. So when you see this blue tick, it means that this account has gone through a process of verifying their identity and they are who they say they are. So these are some of the tools we are building in order to bring more awareness. There's many, many more, but just to give you like a brief context. And with all of these different tools, all of these different things, we, as analytics, we have a lot of questions we need to answer every time, you know, in community integrity. So, for example, how do we make our community safer? What else can we build? There is always a thinking process of what more can we build? How do we move forward? And even how do we define success in a problem as integrity? You know, questions like how many fake accounts are out there, they're not as trivial as you would imagine because you have to define fake accounts, maybe you miss a lot of them. So even that, the number of fake accounts, it's a very hard and complex estimation to make as analytics. And also, how are we doing? Are we doing well in catching them or are we not doing well? How well do we want to be doing in 6 months? Of course, the goal is to have 0, but is this a realistic goal? These are all questions that they need a lot of thinking and a lot of processes to be put in place. And as analytics, we also always have, you know, try to understand different behaviors, as I said before. Like things of, for example, if people change 5% more their names this week, what does it mean for us? Is this something we need to look into? Is this a signal that would give us more input about having more fake accounts or people having a weird behavior, and why are they doing these things? And then when we launch things as well, it's always, you know, Facebook is very, very data driven. So we always go through experimentation process and try to, okay, should we launch this feature? Does it make sense? Where is it gonna help us? If it doesn't help us, how can we improve our classifiers? How can we improve our machine learning? What different features can we use? How does this new thing help with our current goals? So analytics, we are very, very much integrated in community integrity and in every team actually, but community integrity is really analytical heavy. Every team has a lot of analytics people that we always try to guide the product and try to understand and get more and more insights about what's happening and how we can actually improve what we have and how we can be better. And to give you here, I want to give you a bit of context of what does a data engineer do, but also how we integrate with data science and what are the differences we have. So you see this chart, and as you see, data engineering is a bit closer to software engineering and data scientist is a bit closer to statistician. But actually data engineering and data science, we are really, really close together and we build the analytics teams. Like in my team, we work integrally with our data scientists. We collaborate on a daily basis. Anything they build, anything we build is very much related. We take decisions together and we drive the product together. As a day-to-day job, as data engineers, we imagine we are very much integrated in the start of the data. So where the login starts, we want to make sure that the login is there. And then on top of the login, we would build many different pipelines and aggregate the data and try to create data models and tables that are very easy to use for our product teams, for our data scientists, for our software engineers. So we built on top of the logging data sets that will be usable for everyone. And then we try to optimize the queries, build different frameworks that will enhance and make our data life easier. And we'll build a lot of dashboards that will give insights and also detect anomalies in the data and different patterns and give input very fast. And the data scientist will utilize all this data and will help more in creating goals and complex metrics that define success of the product. They would design the experiments for engineers about what are the right metrics to track when we have an A/B test and when we want to launch something new. What is the opportunity? What is the size of a problem? Try to find different roots and causes of different issues that happening. Like if I build an alert, for example, about, okay, as we said, 5% of people change more their names, data science will try to understand where is this coming from exactly? What could be the root problem of this? And also build a lot of predictive modeling and different things. But having said that, it could be very often that we would mix things, and maybe data scientists would also build dashboards or a few pipelines. And as data engineers, we might be involved in experiment or opportunity sizing, because our skill sets are quite similar. And then according to how much analytical you want to be or how technical you want to be, there's always an opportunity to mix and have different roles and create together. So if we talk a bit about the data engineering mission, so as we said, we are involved from the first steps of the life of data, right? So where the data is logged. And with all of these logs and all of these data streams that we have, it's very often that, you know, the data might not be validated, they might be incomplete, we might have too much data, they might have different ways of different granularities, might be inconsistent, and imagine having lots of inconsistencies across all the problems and all the different areas. So as data engineers, we want to make sure that the data is coming correctly, they are consistent, they are complete. We also want to optimize for efficiency and make sure that the data is accurate. So we are building a lot of these processes. We work very close with engineers to make sure that we have everything we need for our teams and for what we want to measure. And we will build pipelines on top of the loggings and create, you know, our core tables where we will have data for all of these patterns, for all of these metrics, and have our anomaly tests to see, okay, is the data coming duplicated? Do we have more data? Do we have, did somehow we have more rows than what we should have, we expected? And build also dashboards where we can take decisions very easily and we can inform our teams and everyone will use across the company to see how we are doing and take and drive the product forward. So with all of these different data, different products, different problems, there's lots of trade-offs at work we need to do always. And that's where we come to understand, okay, what is more important for us? How do we work and what trade-offs do we have to make? So the first one I put here is accuracy versus time, right? So what does that mean? So when we say before we have hundreds of groups, millions of groups, billions of users, imagine having to understand all of the clicks that people are doing every day and what does it mean? Are they bad or not from their behavior? And imagine having to understand all of this data. How they're massive. It's a massive, massive amount of data, and manipulating this data takes a lot of CPU time. So in other teams, apart from community integrity, accuracy versus time, this could be handled by downsampling the data and getting few samples of all the data. But in community integrity, the things we're trying to identify are the outliers, are the bad actors. So downsampling the amount of data actually wouldn't help us in what we're trying to solve, because we would get a sample and we would this sample probably wouldn't include all the edge cases, all this weird behavior that we're trying to find about. So in our team, we want to crunch all of the data sets in minimal latency. And that's Facebook, and that's why Facebook has pioneered the infrastructure for distributing computation across a cluster, and our CPU time for querying data does not equal the real time of querying data. So Facebook has developed Hive and Presto. They are both open source tools, and Hive, it translates data queries in MapReduce jobs. In that way, they allocate the queries to different MapReduce jobs, and it really, really reduces the amount of CPU time that we use. And then Facebook also developed Presto, which is extremely, extremely fast, and it doesn't write intermediate steps to the disk, and we can query terabytes of data in matters of minutes, and it makes our life much easier. You still need to be careful. You still need to have a good knowledge of how to use these tools and know all the tips and tricks for your query to not fail. But it's very common, once you start dealing with this data. I think my first weeks or months, I would run a query and it would run for hours, and I was, okay, what do I do now? How do I understand this data? But actually, once you learn more about the tools and you learn to utilize them the best way, you can actually do your work really fast in massive amounts of data. Then we have FB Learner as well. This is an internal tool, and it has a lot of distributed machine learning tools that we can do a lot more advanced computations. We use for our classifiers, and we train them there, and it also works really, really fast and helps us reduce a lot of the CPU time. The next trade-off here I have is accuracy and analytics time. So how many analytics people we have, and how accurate we want to be to the problems we solve when we have a lot of problems to solve, right? And it's always a question, choosing what are the problems you have to answer, how deep you want to go, according to how many people you have, because there are so many different problems, and we could potentially spend a lot of time deep diving in many, many different things. So for that, in order to remove ad hoc time and, there is a lot of repetitive work and a lot of ad hoc things and new questions. So we try to build a lot of self-service tools, also as data engineers, also as software engineers. So all of our tools, we try to make them scalable for many different ways of usage. So one example here is an experimentation tool we have across the company, and it's built from a specific team. And what does it do? It takes a lot of ad hoc work for when you have to do an analysis about an experiment. So what do? Is we define evaluation metrics. The data engineer will build tables for these metrics, and we would input them to this tool. Then we would define the exposure that we want to have and set up the logging. And then the framework, the experimentation framework, would automatically aggregate the exposure logs. It would join on its own on the fly the metrics. It would evaluate the statistical test and tell you, is it significant? Is it not significant? It would plot confidence intervals. And we have also a UI tool that you can search and visualize almost real-time data. So this would reduce a lot of the trivial data pull requests from cross-functional partners. And however, still, you know, we have these automated tools and it's really great, but still data scientists and data engineers, we have so many questions to answer, but we still try to optimize for the simple things and the things that we can automate so that we as analytics and as teams, we can actually think bigger of bigger problems and go and solve the most problems we can. The next trade-off we have here is agility versus reusability. So this comes down to how we want to structure our teams as analytics, as data engineers, as data scientists. How do we support best our teams? So there are different cases of should we integrate in the product team as a data engineer and then have agile development, have faster communication with our cross-functional teams, or should we have a separate data engineer team as a service and have a more strategic collaboration and identify more generalizable solutions? So for data engineers, the answer here is different for every case. We have both. So I am working in my product team and I'm working really closely with my engineers, my data scientists, and I build products for my team. And if the products are adaptable to a larger framework, I try to scale them and I try to build tools that are generalizable to the whole community integrity or other teams. But we also have core data engineering teams that are focused on just building tools and just building core data sets and core data infrastructure for all of the company. So as data engineers, we have both in order to be agile and in order to be more strategic. Our data science teams are integrated. Every data scientist is integrated in a team, and it might be more than one data scientist at a time in a specific team, but data scientists are more integrated in one team. They work very closely with engineers and product managers to solve different questions. So Facebook is very flexible in the structure and always tries to find the best way to serve our products and our teams. And in order to build successful products, we have this flexibility and different working models across teams. The final trade-off I've put here is relevance and coverage. So what does that mean? We have thousands of employees and we are working across all over the world. I've collaborated with people across everywhere from Asia to US to Europe. So we have people everywhere. And that's why we need to, in order to best leverage our work, we want to be able to communicate effectively and efficiently with everyone without also overwhelming ourselves with a lot of irrelevant information. So how would we best do that in order to have a good communication with so many people and also not feel overwhelmed? Facebook is a social media platform and it already had the technology to match contact with people. So that's where Workplace was born. So Workplace is the internal tool, the internal platform we use in order to help co-workers and to communicate with each other. So imagine it's Facebook for work, and that's where we all communicate. So we don't use emails that much, we don't use Slack or other things, but we have Workplace, which is like Facebook. So we would have our own groups, we would exchange messages with each other, We would post things or share our ideas, and then you would try to find the relevant information for you, and you can follow the things you want to follow. And we have built this culture of having the social media network in our workplace. So the discovery is much easier. You can search for things, you can find things there. You might even discover things that you didn't even know about, or engage in different conversations and in different groups. And also, it's a great way to distribute, discuss best practices, and reach out to the right people, because you can find from the groups and everything who is the right person and who has done anything similar on what you're looking for. Okay, so I'd like to share a bit now about what makes a data engineer. So common fields of study, as it says here, is software engineering or computer science. Having said that, I never studied computer science. I studied mechanical engineering, so I come from a different background. But I really love data. I started doing some research in my university, and I was querying and I was getting data from a Twitter API, and was doing some Python, and was learning some things on my own. And then I just found my first job as an analyst, and then it transitioned to data engineering. So you need the engineering skills, and you need to have this love for coding, I guess, and for digging into things and for data. And software engineering and computer science background would definitely help, but it's definitely not the only way you could get into a data engineering field. I think one good example in our company is we have someone, she comes from a philosophy background, and she just loved learning about coding and these things, and she got the job. So you need to have a coding ability. We use different languages. Python is very common, but also any other languages are also welcome. I think it's more about having a coding mindset and understanding best ways to utilize data and manipulate data. SQL is our everyday language. Our second language is SQL. We know it by heart. For data engineering, statistics are on a basic level, I would say. Of course, you need to understand, but there is no requirement of you going very deep. It's mostly for a data science role that you might need a bit more depth in statistics. And you need to have a good product sense, let's say, a good reasoning to understand complex data, and try to be curious about, what do this data talk to me about? What do they tell me? What can I find more from this information? So it's really important to be curious and to, data can be your intuition to understand problems, right? It's your new reasoning, it's your new sentence when you have to drive a product. If you can back up your decision with data, then there is no excuse for someone to not do what you want. So you need to understand these reasons, and you need to be able to see through the data. So how can you join Facebook? We have internships. So our facebook.com careers, you can find many ways and all of our open positions. And even during COVID, we've kept hiring people, and we have a lot of new people joining. Remote is a bit harder, but yeah. For example, I'm an intern manager this summer, and my intern is completely remote. It's the first time we are trying to do this, but it works, and we still have lots of internships. They're usually summer internships, but if you're interested, you can already have a look and see. Our internships last for 12 weeks mostly, and they're paid summer internships, and then you have a project developed from someone in the company, and it's focused on you, and you work on this project for 12 weeks. We have Facebook University, where it's a shorter internship. And of course, we have full-time jobs and full-time roles, where if you're a graduate and if you have some work experience, you can apply for a proper data engineering role or a proper data science role. Yeah, but have a look, and I'm happy to answer any questions in case you have. And as a closing thought, data is so important. Like you're all here in this data science conference, so I hope you're also really excited about data, about how much they can tell you. For me, when I found the magic of data, I was really, really amazed with how many things you can understand. And I really feel the data never lie. You know, once you find some adversarial behavior or something missing, there is an opportunity there for you to change something, to fix something, to optimize something. There's an opportunity for you to drive something. Building goals and building data-driven decisions can really make successful products. So always look for the opportunities where data are not properly utilized, and build these opportunities for your work and for the things you're passionate about. And use data as your backup to encourage ideas, democratize, and be open and ready to be surprised with data. Yeah. Thank you, everyone. And I'm gonna leave this as a closing slide with these are some of the posters we have at our office at Facebook, and some different ways we move fast, begin anywhere, ship low, be bold. Thank you. Any questions?
Thank you very much, Nasia, for a very good presentation and enlightening about being a data engineer. That's really very good for our aspiring data scientists and data engineers from the DSA community. Yeah, so any questions, please shout out your few questions to Nasia. We still have her online. Yeah. Okay. She has really highlighted what it takes to be a data engineer. Okay. At Facebook, massive data sets, complex
A lot of data, yeah.
databases. Yeah. So you're all welcome to with any questions. Yeah. There's a question here for Maureen asking if you can expound more on anomaly detection. How is it handled? Yeah.
Yeah, anomaly detection. So since our systems are quite complex, and we have many different layers where things can go wrong, we try to put these checks and try to have anomaly checks on data and metrics at all stages. So imagine we would set up at the first stage of the logging anomaly detection on the data, and this anomaly detection would be maybe simple checks like count number of rows, and if these numbers of rows change very fast on one day, then this would trigger an alert and we would get notified. If we have things like we missed this amount of data for a specific day, again, we would have to check what happened in the logging side. Then we put, like if we have duplicate rows, we would, count different rows on a specific grain and also measure their anomalies. And then we would have anomalies also on the tables we build as data engineers for similar checks, count of nulls, count of zeros, duplicates, but also we put anomaly checks on our metrics. So if our metrics move outside of a specific, it could be either a threshold, let's say if the metric goes below 0 or above some number, then we would get an alert. But also if it has, we have a calculation where if the metric moves outside of a specific range or confidence intervals, then we would also get an alert and we will try to debug what happened. So we have anomaly detection on all the life of data, let's say, in order to try to be proactive and understand where things might go wrong, logging, data modeling, or the metric side, and in order to see if it's a real movement of the metric, because something actually happened and we have some investigation to do, and maybe there is an attack of fake accounts or someone broke our system, or it might be just a data corruption or some data leak or something like that. Hope this answers the question.
Yeah, thanks. I think Maureen, you've answered, you have got good feedback. Okay, any other question? All right, no other question for Nasia. Any question, feedback from the other panelists on Nasia's talk? Yeah. Yeah, just out of curiosity, how many data engineers are there at Facebook?
Oh, across, I'm not sure, like a lot. I think in London, we are around 60 in the London office.
60.
I would lie if I know the number across the world, because we have, yeah, it's, I'm not sure, maybe 700, I would assume something like this, a bit less than 1,000 data engineers. But it's an org that is growing. As data engineers, the org started 6 years ago. So in the past, it used to be software engineers doing the role of a data engineer. But then Facebook realized that it's actually, we need analytics teams to be more robust, and we need specific data engineers to tackle these problems. So when I joined 2.5 years ago, I was the first woman in London. And now the team has grown a lot, and we have more women, and we have more diversity and more people joining. So it is growing, but yeah, it's also it's fairly new for Facebook.
Actually, we just have another question about what it takes to hire a data engineer at Facebook. Do you hire, when you mean different backgrounds, is it ethnicity or discipline, academic discipline? I'm not sure whether, I'm not quite sure what he means there when he says data engineers from different backgrounds. If they can be hired by Facebook, but I'm not sure when he talks about the different backgrounds, whether it's academic background or ethnicity. Yeah, if you can answer on both. Yeah.
So both, yeah. So I have a different background. Like I'm not a software engineer. I haven't studied computer science. I've studied mechanical engineering. And I never thought I would go to Facebook, to be honest, right? Like I come from Greece, so it's not a country that I would be very, it would be very easy to go abroad or have the capacity to, I don't know, to like, you know, people in the US, they have more opportunities to see these roles. I never thought of myself I would be in Facebook. And I ended up there. So it took for me, I guess it took a few years of work experience to get a job at Facebook. But I think if you don't have experience and if you study, applying for an internship is the easiest way to go through a Facebook role of data science or data engineering. For me, I ended up, because I really liked analytics, I ended up having a job of an analyst, of a business intelligence analyst, and then it evolved more towards the data engineering. And then after 3 years of working, a friend of mine referred me at Facebook who was working there, and I got the job. That's how it happened. So there is no, the background doesn't matter. The experience and the passion might matter. And also, of course, if you do an internship, the university must be relevant. But if you don't do an internship and you just have some analytics experience, you can always apply for Facebook. And of course, the ethnicity, it doesn't matter at all. I think the opposite. We are really, really trying to hire people from all over the world and bring all the different diversity and the voices inside the company, because otherwise we can't build products for all over the world. It's going to be very biased, and we try to fight this from the inside. Yeah.
Thanks. Maybe the last question I would ask is, how is the interview for data engineering post at Facebook like? What does one have to prepare for? Yeah.
Yeah, so the skills that you need for the interview are SQL and Python, or it could, so SQL for sure. The programming language, it could be Python, it could be Java, it could be Scala, it doesn't matter. But we need very strong SQL, we need some strong coding skills in any language. And then you need to be prepared to have different case studies about, not case studies, but to show your analytics skills about, you know, how would you develop different metrics? How would you handle different situations? How would you build a data model? And how would you build an ETL? So I think this slide that I showed before, I will also, I think you have the slides as well, but it's about, you know, as a data engineer from the start, what are the metrics you define? How would you build a data model? How would you do an ETL? And also show the skills with coding, SQL. That would be sufficient for an interview. The internship interview, I think it's it doesn't require that much. It's more about a bit of SQL and a bit of coding, but it's not as comprehensive as a full-time employee role. Yeah.
Thanks. And actually, there was another comment from Haben saying there are different scholarship opportunities in data science. However, the biggest challenge from applicants from this side is getting good recommendations. How do you help? How do you address that? Yeah.
So I'm not sure about the data science scholarships. I think if this is something that is of interest, I can ask and I can send you a response afterwards, because I'm really not aware of them. How works and the recommender.
Yeah, there are many which are announced out there.
Okay.
There are many which are announced out there, but actually applicants from this side of the world and from Africa are disadvantaged when it comes to getting good recommenders.
Let me try and ask my, I know the girl from HR who is like organized and brought us in contact. So I might ask her and like try to send you some feedback afterwards and see what does she say. Yeah. Yeah, this is, yeah.
Okay. Yeah, thank you. Thank you, Nasia. I think I need to, is it Martin or Joyce? Do we break or we continue with the talk from Shalmali?
I think we just stretch a bit and then we can continue with the talk.
Okay, so exactly, yeah. So we go get a coffee, get a cigarette, stretch a bit. We'll begin at 15:45. Yeah, we'll resume at 15:45. Yeah, for the second session, for the last session of the summer school. Yeah, we'll take a small break. Thanks. But the meeting room will still be open. Yeah, in case you have any questions, you can reach out on the chat to the organizers or any question. The meeting room will remain open for during this break. Yeah, we are excited. I'm sure everyone is back from the break, and we are all geared up for our last talk on this summer school on ethics in ML for healthcare from Shalmali Joshi. We are very glad to have her. She's a postdoc at Vector Institute. Yeah, you're welcome, Shalmali.
Thank you. Can everyone hear me?
Loud and clear.
Okay, great. So thank you for giving me this opportunity to give this talk. I'm very excited. I generally dabble as a postdoc at Vector Institute and work in causality, interpretability, and some fairness work as well, all in the context of healthcare. I know this is the last talk and everybody must be tired. I'm going to keep it light and breezy. And I really want to just focus on how to operationalize thinking about ethics when you are looking at a machine learning or a data science pipeline in the context of healthcare. It's not going to be comprehensive, but it's going to be more pragmatic. So let me get started. What I'm going to talk about is how do we even start thinking about ethics in the context of healthcare, because there are so many things to think about. And one of the things I will try to ground it in is in the concept of bioethics, which is essentially the ethical framework that, that healthcare practitioners use to ground their practice, okay? And then I hope to convince you that this is also relevant to doing good data science and good machine learning for healthcare. The way I'm going to do it is break it down for you into every step of the data science pipeline and how we might want to start thinking about where at each point in the pipeline you might have some ethical questions that you might want to try to answer before you proceed, okay? And this can happen during data collection, when you pre-process and explore your data. These are very standard things we do as data science practitioners or even researchers. And then you try to build your model. And within this model also comes the context of what is known as algorithmic fairness. And I will try to convince you about when and when not it is relevant to the context of healthcare. And finally, I will try to convince you that we need a little bit of an out of the box thinking to be able to ground healthcare even more in the context of ethics as we have it today in machine learning. Okay, so let me get started. Healthcare as a practice has a lot of history on operating out of specific ethical principles. And the reason is that we as clinicians, as public health professionals, you are going to affect policies that affect individual lives. And therefore, you have to have some model framework which you essentially guide your practice by. And the four main principles are known as non-malfeasance, beneficence, justice, and autonomy. What does non-malfeasance mean? It means that you should not do any harm to anybody by making the kinds of decisions you're making. Okay, and beneficence implies that you have a duty to do moral good to everybody involved. And justice is the closest to what we understand as fairness, which is essentially if somebody is equal to each other, they should be treated equally well. And finally, the concept of autonomy is also very important in the context of healthcare, because you have to assume that in the end, it's the patient who has the most power to decide what is the best set of actions and decisions for them. Okay, now the question will be, how do we think about this in the context of health data science? And I'm going to argue that this happens at every step from where you get the data from. You are touching individual patients. It might be complex data, it might be sensitive data like mental health status. And so we are touching on the privacy of individual patients when we do this. So you want to be very mindful of that. It's also about data collection. Whose data has come all the way into your nice table as a row is an important signal, okay? And even this is a context that goes beyond just doing data science, because even what is considered as gold standard within healthcare is randomized control trials, which is essentially going to tell you how useful any kind of intervention is, like a medication is or a vaccine is, on the population. Even these kinds of gold standards have generally not lived up to the expectations of how generalizable they should be. And the moment you start trying to replicate all of this within the context of health data science, these problems of representation can become bigger and bigger. Okay, so you want to think about who is coming into your table and your big data set also. There's a lot of gap in clinical knowledge. We don't have scientific evidence for all the things that are happening to us right now. And you can see that even within the context of the pandemic that has hit everyone. So for example, think about heart attacks. Women have different symptoms when they get heart attacks. And until very recently, we were ignoring heart attacks much more often for women because women just didn't understand they were having heart attacks when they did. So we have gaps in clinical knowledge. And when you take those rules and labels as gold standard and put it in your data science framework, we are likely to automate that gap in clinical knowledge as well. Okay, so these are important things to think about. There's also much more important a context, which is healthcare happens outside of the hospital. It is essentially how you are treated, what your socioeconomic status is, which determines your long-term physiological pathway much more than what's happening in those hours that you are spending in the clinic or the hospital. And how these mechanisms are changing is not as well known in all contexts. And that also starts affecting how we should do data science in health. And finally, when there are existing labels and scores that we use, there's a lot of such scores. Framingham risk score is an example, which is used for predicting, say, risk of cardiovascular diseases. There is the score that I'm showing you here on the slide is what is known as the risk of what is the potential of having a vaginal birth after a woman has a C-section. Now, inadvertently and unintentionally, people have created these labels which already have bias embedded in them. So this particular score, when it comes to the United States, they have included ethnicity information because at some point when they did their research, they found correlations between somebody being Black and Hispanic to the risk being higher when giving vaginal births after C-sections. But the problem is we don't know why that was the case, and just unintentionally including that as a feature in your risk prediction is unfortunately led to a bias in how these scores are even assigned, which means that generally Black and Hispanic women have been told that they are at a much higher risk than their white counterparts when they are trying to give vaginal birth after C-section. And recently they have found out that that is causing an unintended bias, and now that is being corrected this year. So these are the unintended consequences of using existing scores blindly into our data science frameworks. So we really need to understand how things are operating to be able to do good science. Okay, so now I'm going to break this down into how we can start thinking about doing better data science within our own practice of doing good healthcare. So let's start from all the way from data collection to pre-processing and model design. I'm not going to spend that much time on clinical validation and deployment because challenges until here are a lot, but I hopefully will leave you with some thoughts on how we might want to start thinking about actually leveraging things that we know how to do well in machine learning to be able to address these challenges. Okay, so let me get started with data collection. And what you as data scientists should start asking when you are going to start looking at hospital data or data from a clinic or even public health data, you have to ask why the data was collected in the first place if it's just being given to you. If you're not actively collecting the data, then it's very likely that in the hospital, it's happening for administrative reasons. And the clinical signal in that is generally lower. And this is definitely a problem, even in large hospital systems, which might have massive electronic health records already in place to collect data. Okay? Now, as I said, who gets into the hospital system is a big signal, because it is generally tied to their capacity to make it to the hospital, their socioeconomic status. If a person has to walk go 50 kilometers to get lab tests done, it's unlikely it's going to make it all the way into the record of the patient. And so it introduces a lot of confounding that will affect how your outcomes are being predicted. Okay, even missingness, as I said, it can be indicative. Maybe a person just cannot afford to make it all the way to the hospital. Okay, maybe they do it much less often because the hospital is far away. And so missingness is indicative and is generally not random. Okay, as I said, in the case of heart attacks, even all that bias is baked already into the labels that we have seen for patients. And that's not just true for gaps in clinical knowledge, it can also be true for how clinicians might be practicing healthcare. Okay, and all that is gone into your data already that you're seeing in a nice clean table. Okay? Something as simple as changing data collection platforms can have significant changes in the way the data was collected and can introduce data set shift, which is a machine learning problem and a challenge that we don't completely know how to address. But this has been shown by evidence that when EHR systems change between hospitals, suddenly the way the data was looking changes, and it suddenly changes the way the machine learning model starts to behave on simple prediction problems as well. Okay. And the last thing you should think about is how well whatever you learn is going to perform if you decided to deploy it in, say, another clinic or deployed it 1 year later. Okay, so these are the kinds of questions you want to start asking upfront. Okay, the next step is you're going to do some pre-processing. You will have missingness. You should check for missingness rates across different subgroups. Maybe you have more missing data when it comes to women or a younger population or a much older population. Then you can do some imputation. But as I said, which is a general practice we do in data science, I have done that when I pre-process my health data. You have to know whether you're making more mistakes when you're doing imputation for certain kinds of subgroups. Okay. And this is easy to check by just running some simulations. Maybe you can create some simulated data and then change the number of samples that you have from specific groups and see how well or how badly you do when you do imputation. Okay? These kinds of practices are going to help you understand where the mistakes might be coming from, even in a complex data science pipeline. Okay. The next thing we might want to do is we are used to coming up with good feature representations, which is what deep neural networks are very good at. But the problem is that they have a lot of bias in them. And that also has been evidenced very widely. And later on in the talk, I will show you some examples of how that translates to biases in the clinical context as well. So you have to think about whether your feature representations are good for the job that you are looking for. Okay. There's also unintended confounding that comes out. Now, there's also work that shows that when deep neural networks or convolutional neural networks were used to diagnose pneumonia from chest x-rays, they were actually much better at figuring out what hospital that data is from because of certain marks that metadata that gets attached to these x-rays. So the convolutional neural network ended up focusing on the wrong things instead of what is clinically relevant, unfortunately. So these kinds of problems happen a lot in healthcare, which is why we are still far away from a lot of success in deploying these kinds of methods in practice. Okay. And the best way to understand these kinds of challenges is to go and talk to the clinicians and everybody involved consistently and during every step of the data science pipeline. Okay, so it's not just, I said a little bit about how our outcomes or our labels, we can be biased, but it's not just that the outcomes are biased. It's the way we treat patients is also potentially biased. And this can be shown even in the context of something that where we don't expect a lot of bias. So for example, if a patient gets very sick, they are admitted into the ICU, they are given very specific kinds of interventions like ventilations and vasopressors. These kinds of things are very standardized in clinical care. There is no reason why you have to treat adult men very differently from adult women, or different kinds of ethnicities very differently. Most of the clinical guidelines are fairly uniform. But cultural context comes into play. And this is a case of the United States, where generally historical mistrust exists in the healthcare system on behalf of Black patients, which is essentially very much justified. But what does that do in the kind of practice that clinicians incorporate into their daily practice? It essentially happens that patients within specific groups tend to be over aggressively treated, even when they can't handle that treatment, particularly in the context of end-of-life care. So it's not just about outcomes, it's about how interventions are done on patients. It can be very different depending on cultural context. Okay, so you have to look out for whether that has happened in your data as well. Okay? And that can be done with simple data exploration. So it's not an impossible problem to figure out whether these problems exist, but you should be careful about thinking about these problems and actually going and doing that in your data. Okay. So if you've done that, you've convinced yourself that the data looks reasonable, now you're going to start training a model on it. And then what should you think about when you are going to do that is how you are performing across different subgroups that you care about, like men and women in the context of, say, heart attacks. How reliable do you think that risk estimate is coming from your logistic regression model or your deep neural network, which throws you a softmax probability? How do you know that that's actually a meaningful one based on which you should decide to treat a patient or send them home, for example? Okay, and then you should decide whether you can actually generalize that to younger populations, which is unlikely to happen because sometimes symptoms manifest very differently in younger populations compared to adults. Okay, so you should ask yourself these questions, and then you can actually start doing some kinds of exercises to figure out whether that's actually happening. And this is a case of looking at unstructured clinical notes, which you will likely do in your data science pipeline very often. You will take clinical notes, you might run topic models on them, figure out how the context that the clinical notes are talking about. You'll come up with an embedding or a representation, and then you will put it into your neural network to get a prediction on whether a patient might die or whether a patient might get readmitted into a psychiatric ward because of the kinds of symptoms that are being shown in the note itself. And what these authors show that the moment you do that, you are seeing different error rates for different subpopulations, male or female, depending on the kind of insurance they have, as well as racial groups. Okay, so the moment you start looking at these questions, now you're seeing that maybe it's happening because you have fewer female patients. Maybe you have far fewer people on public health insurance, but you have to go back and understand whether that is the cause of the error rate itself, or you might need to collect more data because you might have more missingness for females or people with public insurance. Okay, so these are the kinds of questions you can start asking. And that's when the relevance of the subfield of algorithmic fairness comes in. Okay, so I think we've convinced ourselves that data is biased, messy, and the field of algorithmic fairness is essentially designed to mitigate the statistical effects of these kinds of problems. Okay, and I'm going to go through a brief tangent of what these kinds of methods generally do. I'm not saying all methods do this, but the kinds of trade-offs that these methods make are sometimes in complete violation of the bioethical principles that we started with. Okay, and that is why we have to be very careful about when algorithmic fairness is actually relevant to healthcare data and when it is not. So let me start with an example, and this is like probably the most technical part of this talk, which is essentially just formalizing what is the task that algorithmic fairness generally tries to solve. We'll take our features X, we want to predict some label Y. Maybe you want to see, in a non-healthcare context, maybe you just want to see if somebody gets hired in a job, but in a healthcare context, you might want to decide whether a person has to get treated, whether the person has to get discharged from the hospital or get some other intervention. And then Y hat will be your model prediction. And then you are going to look at performance across different groups that I'm going to show with the alphabet A, which can be a racial group, which is a social construct, but used widely as a categorical variable in the context of algorithmic fairness. It could be biological sex, it could be gender, it could be age, it could be socioeconomic status. Okay, and most of what algorithmic fairness does is try to figure out whether the performance across these different groups is similar. So I can look at performance of the model that I will train, this particular neural network, is similar across men and women or across age, if that's clinically justified, or even racial groups. Okay, and you might want to think about different kinds of errors that you might want to equalize across different groups. So one of the things that group fairness or algorithmic fairness people are interested in is looking at out of all the patients you predicted could be discharged, how many of them truly do a successful discharge and don't need to be readmitted, is what is known as predictive parity. Okay, you might be interested in looking at false positive rates. So by now I'm going to assume that you are familiar with looking at these kinds of confusion matrices, which are essentially just showing you different kinds of errors that can come up with when you've trained this classifier using your favorite model, and you want to optimize for different kinds of error rates across, say, men and women. Okay, and then finally, you can just look at how many percentages of people I even selected across different groups, men and women, to have the label 1. Now, the way these algorithmic fairness methods do all of this is by making trade-offs between how the performance looks like for men and women. And generally, it involves the trade-off of the kind where you start making different kinds of errors across different patients in these groups. Okay, now the moment you're starting to make different kinds of errors, that's a telltale sign that we are likely to violate the do not harm principle that we started from, because you cannot improve performance for women at the cost of violating do not harm for men. That's not something we can do in healthcare. And that's when you should start thinking about whether that starts to make sense to apply to your data blindly. Okay, and you should be very careful about applying group fairness methods. Now, this is slightly different from individual fairness, but there's a temptation to start using algorithmic fairness in healthcare data, but we have to be very, very careful of doing that. So just as a caveat, there's lots of other fairness definitions I cannot go into without doing them justice. But all of the time, you have to remember that there are trade-offs of most of these methods. So ask the clinician whether these kinds of trade-offs make sense and then actually do it. Okay, sometimes they are important, but most times there are other things you can focus on to actually address the ethical problem there. Okay, so we talked about bioethical principles, and then we talked about fairness. So what about other bioethical frameworks like beneficence and non-malfeasance, do no harm and do moral good? Can we actually come up with sort of mathematical formulations of these and then call it a day and say, think of healthcare as being healthcare as being like successful in terms of formalizing other challenges in ethical healthcare. And people have tried to do this. And there are a couple of ways to think about it. There can be loose connections between principles of do no harm and principles of do moral good by coming up with what it might look like for any given classifier. So you can put restrictions on what classifiers look like. Your favorite neural network can be trained not just for the entire population that you're given to come up with some solution for. You can do it for all the groups that you care about. So men, women, you can train a separate classifier for them. You can also create a separate classifier for young males versus old males. You can create a separate classifier for young women versus old women. Okay, but you might run into this issue where you have far less data for young women or maybe even old women or some other group that you're interested in. So at what point do you consider that these principles are being addressed by learning these models separately for each of your class of interest? So people in machine learning have come up with loose connections between non-malfeasance or do no harm to what are known as preference guarantees, which means that you first want to learn a classifier for every subgroup that you're interested in, and they should have better performance than a model that is trained on the entire population of data. Okay, it's trained in a way that does not look at the fact that it is a young male or an old male. It's trained agnostic to that, but it should be something that has the best performance compared to combining the data. And using such principles, you can essentially come up with a framework on where you want to come up with a combined model, where you want to come up with a model on a specific subgroup, and where you want to stop growing these intersectional groups in the first place. Now, I'm not going to go into the mechanism of that, but all I want to say is there have been works that you should be familiar with that try to operationalize other principles beyond just algorithmic fairness in the context of ethics. But as I said, you cannot claim victory by just looking at different kinds of models and saying that they have better performance and than each other. That's nothing can replace clinical validation compared to any of these mathematical formulations of fairness. Okay. So what else has been done in the context of formalizing statistically what ethics might mean in healthcare? There have been risk stratification models. So think of an example where you are trying to predict cardiovascular risk for patients. Generally, you might not have similar performance across, say, men and women. And you trained your model, and as you are very familiar with, you will probably plot the ROC curve and look at that. And maybe you will see that for men and women, this is essentially what the ROC curve looks like. And so when you try to do something like group fairness, what you will do is, let's say you want to maximize predictive parity or equalized odds. What you will do is you will look at where these two curves intersect, and you will use that threshold for both men and women, because that is the group, that is the point where you have equal rates of true positive error rate and true false positive error rate. Okay, so that is what you will do if you were generally doing equalized odds in the context of, say, job hiring or some non-healthcare context. The problem is when it comes to the healthcare context, this is very limiting because different clinicians would want to, in practice, use different thresholds, and we want to ensure that the error rates are the same, not just for one particular risk threshold that you use, which is equivalent to saying that the prediction is binary. A person has the risk or does not have the risk. But in clinical practice, we usually care about the continuous value of the actual risk. So what you want to do is not just look at these kinds of different curves, but you want to make sure that these curves look very similar for different groups that you care about. And this is a hard problem. the more you train your models and the more you look at these kinds of curves, you will start to see that as you slice and dice the population in different ways, the curves can look very different across different subpopulations. It's just that we haven't been looking at them and we just take the overall AUC score and claim victory. But you should look at different groups, different subgroups, different subgroups, and then see whether these risk scores that you are seeing are actually similar, so that whenever you use a different threshold, you're still making the same kinds of errors. But remember, again, by doing this, you are looking only at subgroup level metrics, first of all. And second, you're also making some kinds of trade-offs. Now, in making this shift in looking at these ROC curves that look different to making these ROC curves look similar, you've already made trade-offs into what could have been the best model for each subgroup, okay? And you should be aware that you are making such trade-offs. And so that's not necessarily always the best idea. So I just want to make sure I caveat that group fairness for healthcare has to be used with caution. Because like I said, it's possible that social determinants of health are affecting your outcome, but it's not enough to just see a correlation and not enough to just do a logistic regression and find good coefficients from your gender to your outcome. You want to understand why you're seeing that correlation. And until you do, it's not necessarily an easy decision on whether you should incorporate gender into your decision making in the first place or not. Okay, so how, or the causal mechanism in which how these sensitive attributes actually affect your outcomes and the way you are treated is crucial. But most often, even clinicians don't necessarily know this. And so you have to be very careful about how you actually design your model once you're done with the data collection and data pre-processing. Okay, when I briefly talked about a lot of these group fairness metrics, one key thing that these kinds of methods ignore is that inherently subpopulations are very different. Something like asthma can progress very differently across different populations, and it can evolve differently depending on the kinds of symptoms or the kinds of subtypes of disease that you have. Okay, and these kinds of challenges are not necessarily taken into account. And the main thing I want to highlight is you cannot certify an algorithm to be fair just because it satisfies some kind of a group fairness metric. Nothing can justify that unless you actually validate it in the clinic on like prospective data with, say, a silent trial where you're looking at how the model is performing across men and women. And then that's when you can claim victory that yes, the model is actually justifiably fair. And that's not an easy job to do, but it's tempting to claim that a model is fair just based on fairness metrics, and that is unlikely to hold true. So you should be careful. Okay, so, but what can you do is there are always going to be these limitations. You know, data is not perfect. We're always going to get messy data. So being transparent about exactly where the model should be applied is probably far more important than whether you can achieve any kind of fairness or not, okay? So just tell the clinician that don't use this model on people who are older than 65 years old because the model will not work, and that's completely fine. So being very transparent about the limitations of the model is very, very key, okay? And not just that, be transparent about what you used to train the model, how you evaluated it. Did you just rely on AUC, or you looked at subgroup AUCs or not? How do you think you will evaluate it prospectively? By prospective, I mean, it's always has to be evaluated on future data that's coming in, okay? You cannot just rely on data that has been collected for you by now. You have to put it in the field, not use it for decision-making, but just use it to see how the model might be performing, collect information silently, and then claim victory after that. It takes a while, but I think it's worth it. Okay, and always involve collaborators, clinicians. They know much more about the data and why certain decisions were made way more than what we will ever understand. Okay, so then the question becomes, where should we even use all of these very complex AI and machine learning models if there are lots of complications, specifically ethical complications when we try to do this? And I think there's lots of ways in which we can claim victory by leveraging what AI is and machine learning is actually good at. So for example, machine learning can be used for auditing existing models very nicely. And there's been evidence of that in looking at simple simulations for auditing existing algorithms. So to give an example, this is data collected on millions of patients where an algorithm was used to generate a score, and that score determined whether a patient actually gets referred to a costly care management program in the United States. Okay, now this particular algorithm, we don't know much about it, essentially used healthcare costs as a proxy for health itself. And so if a person is spending less on their healthcare, it automatically decided that that means that the person is actually generally doing well and does not need a referral to the care management program. And that is where the problem was in the choice of the data scientist who decided that a cost is a good label to predict and cost is a good proxy for health. Okay, and what that did was it created a lot of bias in the kinds of referrals that were done for white patients compared to Black patients. Now, it's not that Black patients were generally more healthy, they just tended to spend a little less on healthcare. And that could happen for a variety of reasons. We don't know the causal mechanisms there. But what happened was the moment these auditing processes start to look at what is happening and why the discrepancy, they showed that even when Black patients and white patients had the same severity in terms of chronic conditions, Black patients were less likely to be referred to the care management program. And so they just did a counterfactual simulation where they said, okay, what would happen if this Black patient was white? They saw that far more Black patients would be referred to the program. And so this is the problem with coming up with a label that actually did not make any sense in terms of approximating any kind of healthcare for the set of patients, even for the white patients. And the moment the authors of this paper essentially changed the label from not predicting cost, but predicting number of chronic conditions on average, that bias significantly reduced. Okay, so that is the level of power you have. You just have to change this label Y to something else, and that bias can significantly go down. Okay. This is another way you can audit complex algorithms where there is no way but to use machine learning. There is no technology that can actually create very strong feature representations for something like unstructured text data. You have probably so far seen something like the BERT embeddings. There are so many other embeddings, but in this particular case, the authors used clinical notes from a specific hospital. They used existing word embeddings from what is known as SciBERT, which is essentially BERT trained on academic publications. And then they tried to just use it on data that came from a hospital in Boston based on the MIMIC3 data set, which is essentially data consisting of ICU patients from the Boston hospital. And what they did was they just essentially took some terms. These kinds of terms are very commonly written in the unstructured node. The nurse comes in, looks at what the patient is doing, they have all sorts of abbreviations, like they use PT for patient and things like that. And they just make notes of how the patient is doing and move on as they go through their shift. Now, if you take these embeddings and then you essentially just try to look at what the model is doing when you try to put clinical words into it, if you put in the race token, you put whether it's a Caucasian person or white or African or African American, you get very different outcomes that the model fills up over here. And that is extremely problematic, and it should almost be infuriating that this is happening. And it's very hard to figure out whether these kinds of problems will go away even if you fine tune the data on the data itself. Like, these are existing embeddings, but there's a lot of tendency to just say, oh, let's fine tune the model on my data and everything will be fine. There is no guarantee that that is actually going to happen, okay? So but you have the power to actually audit this. You can run a bunch of tests on whether this is happening, and the moment you start seeing problems, you know you have to take care of this problem in a very different way, and that implies that you cannot actually ship this in any particular context in clinical healthcare, okay? But you can actually do a lot of good things with machine learning. For example, this is Rediet. You probably have heard her give her talk as well. I really like the idea of just using search queries to figure out what is the information people are looking for, and then give the kinds of interventions that people actually need. That does not mean that you, let me just, okay. So when it looks, sorry for the interruption, interventions can happen outside the clinic. And this is the kind of thing that machine learning is good at, and we should try to do interventions outside the clinic. And these are the kinds of things you can use for that, particularly when you're determining what kinds of information people are seeking, provide them with that, and so on and so forth. Okay. What else can you do with machine learning that is so powerful is you can target your machine learning algorithms for people who have been traditionally underserved. So for example, I'm going to talk a little bit about a professor at Columbia University who works on a lot on endometriosis. Endometriosis is a disease that affects, is a problem that affects women, and the way it shows is women essentially have very painful periods when they're suffering from endometriosis. Now, painful periods is just taken as a norm for how women are suffering, but the reality is this can actually have long-term effects on the health of women. The diagnosis delays for endometriosis are can be up to 7 to 10 years, and by that time, women have already lived their lives and gone through very, very painful experiences. And in the worst case, in some women, it can also cause infertility. So part of ethics is removing the stigma around something like this. And the way this professor decided to go about this is she created a research app where women can go and self-report how they're feeling during their periods. And then what she did was she looked at unsupervised learning methods to actually train models, so she could look at how endometriosis is progressing and what kinds of different kinds of endometriosis exist and how are they manifesting depending on the symptoms that women are reporting they suffer from. Okay, so these are the kinds of things you can actually do when you start to think creatively about how machine learning can help, right? So I just want to argue that you want to look at machine learning as a tool to actually think out of the box about the kinds of problems you want to solve in healthcare. So you target underserved population, you try to inform clinical science. How can we figure out when heart attacks are starting to manifest differently for men and women? How do we reduce diagnosis delays? How do we improve maternal mortality? Which is a common problem in Canada as well as the United States, where Black and Indigenous infant and maternal deaths are much higher than other populations. There's an important challenging causal problem here where even the gold standard in healthcare, which is randomized controlled trials, which essentially determine how well maybe a vaccine might work on the general population, don't necessarily generalize that well. And so there's lots of challenges in figuring out how to essentially certify that something will be generalizable. Okay, and these kinds of questions is, at least in my opinion, much more helpful to solve rather than looking at the data science pipeline as a way to employ some measure of fairness. Okay, and with that, I want to end by saying that all of these ethical concerns are going to come at every stage when you do healthcare data science. You should not fear taking responsibility for being the data science who does responsible healthcare. Okay, and you can do that in a lot of ways. You can do that by thinking creatively about the context in which you're operating and what problem is a meaningful one to solve in the first place. And I strongly believe that auditing machine learning models is in your power and expertise. You need to know exactly what's going on in the data to even figure out how to audit these algorithms. Okay, so you have that expertise, and that's when you can do a good sensitivity analysis, a good audit of how your model might work in practice. And when it comes to clinical care, you have to look at not just validating based on your ROC curves or your AUROC. That's like the first step, which you will just determine, which will essentially just determine the threshold that the model may be good enough, but nothing will replace a good clinical validation. And with that, I can start to take some questions now. And thank you all for listening.
Thank you very much, Shalmali. That was a very good presentation and enlightening on the ethics in the ML in healthcare. That's a very sensitive section. With that, I would like Sekou, if you could lead us through the discussions. And if there are any questions from participants, if you could please voice out your questions on the chat. Yeah, there's one asking about whether these concerns are similar for animals.
Yeah, so there definitely are. Personally, I'm an expert only to the extent that I can talk about clinical healthcare. So I cannot talk about biological sciences in the first place. So I don't think I'm in the best position to answer the question, but I definitely think that there are, as just a layman who is interested in these challenges.
Yeah, but really, I could see some of the protocols are really applicable even for veterinary, for animal sciences. Yeah, we have Sekou back. Yeah, Sekou.
Yes, hi, and thank you for a really cool talk as well. One of the pieces for me is so randomized control trials or clinical trials are the gold standard. And a few of us agree with you that there is not enough trial data. But one of the questions I have is, do you have any thoughts about ways to infer, probably with not the same statistical rigor, but if there are ways to infer some kind of support from observational studies?
Yes, so there is a very recent and a very cool paper from a group at Stanford by Nigam Shah. What they did was they took trial data, took at the treatment effect estimates they got from trial data, and then they tried to see whether if you looked at equivalent observational data and you ran simple causal estimation algorithms like propensity scoring and doubly robust estimations, can you get similar observations, which is generally widely applicable. And they found out that there is a good evidence that it actually does. So that is good news in that you can start to now take RCTs and then try to figure out whether you can replicate that information in general observational data by using causal estimation algorithms.
Nice.
Yeah.
in that space, one of the questions, are there data sets that, for example, a community like ours can, in essence, look to in terms of creation? So there are a couple of proposals currently, both within Data Science Africa, but also Lacuna Fund and others are saying, okay, we'd like to support research projects that would complement the work that is out there, the data sets that are out there. Are there data sets that you think would be interesting for this community to think about?
Yeah, I think to a large extent, the big problem that happens is how do we collect counterfactuals to even validate, right? So you have trial data, all of that is going on at the national level, like different companies are doing it. At least in America, you can just go look at trial data by going to clinicaltrials.gov. And you can figure out what kinds of data that was used. A lot of times you can just get access to that kind of data, right? And I'm assuming that you probably do have. Now the question becomes, can you come up with a data collection pipeline where you look at observational data that looks similar to that, but then you start to collect, you have to spend a few resources to start to collect counterfactuals of somebody who looks very similar to the observational data that you already have, but maybe something is different about them in terms of the protected attribute, like the gender. And then can you ask somebody to then, a clinician or somebody else who's a health expert to then annotate that data? It takes a lot of resources, but that's like the kind of, I think, the thinking we should have to start gathering more and more evidence of generalizability. And I think there's lots of projects that are now coming up to actually try to combine resources from multiple hospitals throughout. And I think that will only make this data collection endeavor a little more easy. And I hope that that will be a good starting point for collecting this kind of evidence.
Thank you. And doing it in an ethically responsible manner.
Yeah.
I don't want to hog, but I was only asking the questions because the Q&A so far is a little quiet.
Yeah.
Yeah. Yes,
I have one question.
Yes, Billy.
So can you touch a bit on the role of interpretability on this?
Yeah.
Especially at the dissemination stage.
So I'm a strong believer that nothing will replace clinical validation, not interpretability and nothing. But I think interpretability might help figure out when to actually defer to the clinician or the expert and not rely on the algorithm. So if a model is making some egregious mistakes and that is highlighted by the interpretability metric or measure that you're using, maybe it highlights that a feature that should not be used in this case is being relied on heavily. That's a pretty good sign that maybe the clinician should stop listening to the machine learning model and decide on their own what to do next for the patient. I hope that answers your question.
Yes, thanks.
Okay. Are there any more questions to Shalmali? Yeah. Okay. I really want to thank